Hello and good morning, or well, good afternoon, depending on where you are connecting from. I'm Carlos Marquez, and I'll be your moderator for today's session that we have on energy storage in the US. So you are at the Energy Storage Workshop USA 2022, and well, we're all very excited to be here. We have uh, about 5 hours of insightful content and analysis delivered by experts on these topics. So just so you know, we will definitely be recording the entire thing and sending it to you in a few days' time. And also, I'd like to well, a reminder for those who already know who we are and who have been to these kind of events, that you can send your questions through the Q&A box. So, whilst the speakers are delivering the presentations, you can send questions through the Q&A box. And, we also have a tradition here at ATA Insights, which is that we ask everybody who is connecting as a member of the audience to tell us where they're connecting from using the chat function. So, right. So, well, once again, thank you very much for being here at the Energy Storage Workshop USA 2022, gearing up to capitalize on the energy storage boom in the US. And before we start, I'd like to thank our sponsors, BASF, Celio, Wärtsilä, Arena Power, ATA Renewables, and Sera. So, right. So, I think we've given enough time to those who might be lagging behind. So I think we can start with the workshop. We'll start with the first session, which is the energy storage opportunity in the US, analysis and forecasts. So I'd like to I'll ask briefly for the panelists to introduce themselves. And first of all, I'd like to to welcome them. If this was a live room, I'd ask you to give them a round of applause. So just imagine the applause. So Alex, Omar, welcome to the first session of this workshop. So how are you today?
Hi, Carlos. Thank you very much for this opportunity. Very interesting topic. I am in Golden, Colorado. So thank you, everybody, for being here and ready to present and take questions, hopefully.
Thank you very much, Omar. And Alex, how are you today?
I'm doing very well. We're facing a new heat storm here in California, far western US. And it's always a time where the role of storage becomes very apparent to everyone here, or at least those paying attention to the electric system. So I look forward to sharing insights and hopefully discussing some of the challenges and global challenges like supply chain and other things that are going on around the world with energy storage. Thank you.
Excellent. Thank you very much, Alex. So, well, I think I'll stop sharing my screen now. So Omar can begin with his presentation. So Omar, whenever you are ready, please go ahead.
Thank you very much, Carlos. Are you able to see my screen, guys?
Yeah, I can see it perfectly. So yeah, please go ahead.
Perfect. So I am Omar Guerra. I am a research engineer at the Grid Planning and Analysis Center, or GPAC, at NREL. NREL is the National Renewable Energy Laboratory located in Golden, Colorado. And today I will be talking about energy storage deployment for the integration of renewables, or basically for high renewable energy or power systems, I would say. So first, I'm going to introduce the energy storage problem, right? I'm going to describe this problem. Then I will be talking about energy storage applications and the value for each of those applications. Then I will be talking about the potential path for the deployment of energy storage technologies in the US. Then I will introduce the results from a case study that, or a set of case studies that we did at NREL regarding the optimal storage deployment of course, energy storage technologies for the integration of wind and solar PV power sources. And finally, I'm going to summarize with some conclusions. Well, regarding the energy storage problem, here in this diagram, I try to explain the problem. On the left, you can see a representation of the net load for a CAISO power system with 95% carbon-free energy mix, including 28% wind plus almost 52% solar PV penetration. In plot A, for example, you can see the hourly fluctuation of the net load across the year. Of course, there are some hours in which the net load is positive. That means that the availability of wind and solar PV power sources is lower than the demand. So you need additional generation from conventional power sources, for example, a nuclear power plant, a hydro power plant, a geothermal power plant, or a gas combined cycle power plant, for example. On the other hand, you can see some hours in which the net load is negative. That means that the availability of wind and solar PV power sources is greater than the demand. So basically you have VRE surplus. So in this context, we may use energy storage technologies to do the shifting of this VRE surplus to hours in which the net load is positive. For example, in plot B, you can see how short duration energy storage technologies, for example, a lithium-ion battery, could be used for the intraday shifting of VRE surplus. Then if we move to plot C, now you can see how long duration energy storage technologies, for example, compressed air energy storage or pumped hydro energy storage, could be used for the interday shifting of VRE surplus, basically shifting VRE surplus across different days. And finally, in plot D, you can see how seasonal energy storage technologies, for example, hydrogen energy storage, could be used for the seasonal shifting of VRE surplus. So in summary, from this slide, if we want to achieve higher penetrations of wind and solar PV power sources in the power system, we may need a combination of short duration, long duration, and seasonal energy storage technologies to do, the multi-scale shifting of VRE surplus. Now, at this point, we know that energy storage can provide energy shifting services to the power grid, but indeed, energy storage can provide a variety of services to the grid, for example, field capacity, frequency reserve, regulation, voltage support, etc. And each of those applications is going to have a specific set of requirements and also a specific time scale. So in summary, energy storage technologies can provide a variety of services to the grid with a given a specification or set of specifications for each service, depending on the market, for example, and also a specific time scale for that service. And this time scale can be from milliseconds to years, actually. Now, in this slide, I present kind of a summary of the potential value for energy storage. For example, in this plot on the left, you can see a summary of the energy storage value for different applications and also for different power systems in the US. In general, of course, the energy storage value is going to depend on the specific power system or electricity market, on the specific application, and also on the specific technology. But in summary, we can say that high energy storage values are associated with regulation, capacity, or resource adequacy, as well as transmission and distribution applications. So in my opinion, these three applications could be key for the deployment of energy storage today. However, the deployment of energy storage technologies may be different in the future. And in this table over here, you can see a path for the deployment, or let's say potential path for the deployment of energy storage technologies in the future. For example, today we are in phase number 1, in which energy storage technologies are deployed mostly for operating reserve, basically for the provision of operating reserve. Then you have the scale of that phase, and this is for the US, right? Like we are expecting the deployment of around up to 30 gigawatts of energy storage in this phase number 1. And then you also have that these technologies are going to be mostly with 1 hour of storage duration. In general, we can see that the primary services that are going to be the driver for storage deployment are going to change depending on the specific phase of deployment. And also the scale and the duration of storage technologies is going to increase in the future. So as we increase the penetration of wind and solar, we are going to see an expansion of the energy storage market, particularly for longer storage durations. Now, let me talk a little bit about a case study or set of case studies that we did at NREL regarding the optimal energy storage deployment for the integration of wind and solar PV power sources. So in this set of studies, we developed an optimization model to optimize the deployment of wind plus solar PV power sources, as well as the deployment of different energy storage technologies to achieve very high penetrations of wind and solar power sources in the energy system or in the power systems. I am not going to present the details of this model, but there is a publication here on the lower level of the slide, in which you can see the details of this mathematical model that we use for this analysis. So in this analysis, we evaluated the 7 independent system operators in the US. And the focus here was on a 100% renewable power systems by 2050. So in this table, you can see a summary of the projected, let's say, load for each ISO in the US, as well as some existing conventional generation, including nuclear generation, hydropower generation, small hydropower, geothermal, and biomass. In addition to that, we also include different energy storage technologies. We include a short duration, and these are generic energy storage technologies. So we included a generic short duration energy storage technology, SD, based on assumptions around lithium-ion battery technology. We also included 2 different long duration energy storage technologies, or generic long duration energy storage technologies, LD1 and LD2, and LD1 is based on assumptions around compressed air energy storage, and on the other hand, long duration energy storage LD2 is based on assumptions around pumped hydro energy storage. And finally, we also included a seasonal or generic seasonal energy storage technologies based on hydrogen, or assumption around hydrogen technology. And here, we include generic storage technologies because we don't, every technology is going to face different constraints. For example, supply chain constraints, location constraints, etc. So here we want just to include generic technologies and see what is going to be the optimal combination of these technologies to achieve a given penetration without specifying the specific technology that is going to be needed. In addition to that, we also need assumption about, wind and solar PV, CAPEX and OPEX. And here, for these assumptions, we use the NREL's 2020 annual technology baseline. And with this information, we run the optimization model. So the optimization model is going to take wind and solar PV profiles plus cost, as well as energy storage and load information for each power system. And then we are going to optimize the deployment of wind plus solar PV, the deployment of different energy storage technologies to achieve a given penetration of renewable energy in a given power system. So regarding the results, in this plot over here on the left, you can see the results just for CAISO and MISO, because those are the 2 extreme cases that were analyzed. For example, CAISO is a system driven by solar PV deployment, because solar PV is cost effective in California. And on the other hand, MISO is a system that is driven mostly by wind deployment, because again, wind technology is very cost competitive in MISO. Quick summary from this slide, you can see that as you increase the penetration of wind and solar PV resources in these power systems, you're going to see an increase on the optimal curtailment of wind and solar PV. However, when you move to 100% renewable power system, you're going to see a significant drop in the VRE or optimal VRE curtailment. And this drop is going to be driven by the fact that at 100% renewable energy mix, the deployment of seasonal energy storage technologies is more cost effective than the overbuilding of wind and solar PV capacity, because then you're going to have a very high VRE curtailment. Indeed, in this plot over here on the left, you can see the optimal combination of storage technologies for CAISO and MISO and for different renewable energy mix targets. For example, in MISO, you may achieve up to 85% renewable energy mix without the deployment of seasonal energy storage technologies. On the other hand, for CAISO, you may achieve up to 90% renewable energy mix without the deployment of seasonal energy storage technologies. And here I would like to say that, the optimal combination of technologies is going to depend on the specific power system, right? So we cannot say that, just deploy lithium-ion batteries plus compressed air energy storage and you're going to solve the energy storage problem everywhere. That is not the case. And on the other hand, in plot B and D, you can see the optimal storage duration for each technology. And in general, as you increase the penetration of wind and solar PV or renewable power sources in the system, you're going to see an increase on the optimal duration that is going to be needed for each energy storage technology. So with this, I would like to conclude this presentation with some, let's say, key findings or conclusions, I will say. First, the energy storage value is going to depend on the application, on the power system, and on the technology. But in general, we can say that high energy storage values are associated with regulation, capacity or resource adequacy, and also transmission and distribution application. So today, I think, in my opinion, those are going to be, key applications for the deployment of energy storage technologies. We also have that, as I show, short duration, long duration, and seasonal energy storage technologies will help to achieve higher penetrations of wind and solar PV power system in the electricity sector. However, there are other, let's say, flexibility options that we can exploit, but for sure, energy storage technology could be cost-effective for the integration of wind and solar PV power sources. Indeed, we showed that carbon-free and renewable energy mix targets of up to 80% are achievable with economic curtailment plus a combination of short duration and long duration energy storage technologies. Then there is going to be a point between 80 and 95% when seasonal storage technologies are becoming more cost competitive. And of course, this breaking point is going to depend on the specific power system. So with this, I would like to conclude this presentation, and I guess Alex is next.
Thank you very much, Omar, for your presentation. Very insightful. I'd like to encourage people in the audience to send their questions through the Q&A box. And then, without any further ado, I'd like to give the floor to Alex Morris so he can present as well. So, Omar, whenever you can, if you can stop sharing, then Alex will be able to start his presentation. And in the meantime, I know a couple of people have asked that, like, to remind everybody that, yes, we are recording the session and we'll be sharing the recording and the slides with you. You'll get them a couple of days after the event. So I can see your presentation on screen, Alex. So over to you.
Okay, can you hear me okay?
Yeah, I can hear you fine. So yeah, go ahead.
Great. Well, hi, everyone. My name is Alex Morris. I serve as the Executive Director with the California Energy Storage Alliance. So I'll talk a little bit about the Western United States energy storage needs, but I wanted to tip my hat to Omar. Omar, thank you. I think you've set the stage very well. That's very sophisticated modeling and highlights the sort of growing need for a portfolio of storage. And just before we start, California's been a leader in storage, and I'll share more about CISA, but one of the interesting questions I've worked on this week has been, what does a properly built storage toolkit look like for California? So between California and the Department of Energy in the United States, we have, hundreds of millions of dollars being explored to further develop the energy storage toolkit. And that would include the mid-range storage, flow batteries, compressed air, and also longer types of storage. And again, there are many types of storage, including pump hydro and seasonal storage, et cetera. And so we've started on this interesting conversation of saying, hey, the models show it can be cost effective, but what does a properly functioning market look like? And think of your auto market. You have, the right amount of competition in all these different categories, and everybody understands the product and they know how to insure it. There's financing available. And so that's really what a sophisticated, fully designed market looks like. And in the energy storage space, you would say we basically have our passenger car model set functioning. We have the short range storage where you can get insurance and you can go and get it at your house or at your local grid. But beyond that, we still have a lot of need for developing the market, and we're working on that in California. I'm happy to share more. Fundamentally, though, I would say the California Energy Storage Alliance focuses on growing the storage market. It's one of the largest markets in the world, and I'll give you some numbers about it. But CISA has approached this job by focusing first on policy, and then second on utilities and the buyers. And those are the ones who need to understand energy storage, understand its roles, understand how you buy it, understand who the players are, and you get everyone together and you can gradually build a market that way. And so in CISA, we have over 100 member companies. Really this is, I would say, much of the energy storage ecosystem. This is all of the industry that's really serious in investing in California. And if you're not on this list, please come talk to me, because certainly we'd love your help. And I appreciate the chance to work with these companies, all of whom are very smart and very driven. And with their help, let me share a little bit about California and the market. So currently, energy storage across the US, and Omar was looking forward, but currently there's about 24 gigawatts, and much of that is going to be pump hydro storage that's been built for 30 years or more. And we're seeing a lot of project development. So in 2021, 550 energy storage projects were operational. And then of that, you look and you go to California and say California leads the US in storage, 215 operational projects, and these are grid scale projects. There are many small customer-sited projects, many thousands of them. And it totals to about 4.2 gigawatts, so 4,200 megawatts of storage. And that's 17% of the capacity. And that's actually quite large because much of the capacity is old pump hydro. So virtually the vast majority of new storage is happening in California, and then followed by Hawaii, New York, and Texas. And I know it's hard to see from this table, but what this table shows you is that in California alone, they're expecting 11 gigawatts of energy storage needed just over the next 4 years. So to give you a feel for 11 gigawatts, that's more than the entire power system of Los Angeles Department of Water and Power, maybe 2 or 3 times over. So in the next 4 years alone, we will be building out power resources equivalent to serving Los Angeles, say 3 times over. So the amount of development going on here is truly massive. It's never occurred at this scale. And it's really stressing the amount and systems and markets we have in California about how to get storage built. Do you have the right types? Can you bring it in from overseas? Can you interconnect it? And are you upgrading your transmission system? So all of these, what I call execution challenges, are occurring today. Still pretty exciting stuff though, and embedded in that 11 gigawatts. Beyond that, we're also looking at adding long duration. So the state is seeing, hey, we're getting our storage built, but now we need to get that next level of storage, which Omar, I think you framed it very good. I think it was your type 3 storage of your daily cycling storage that absorbs the extra renewables and then shifts it out at night. And we have built storage for peaking capacity, and we're still doing that, but more so we're starting to shift to the next application where you want longer duration storage, more diurnal cycling, or deep cycling as I call it. And CISA did its own modeling. I would say this was pretty early stage long duration energy storage assessments. And the reason we were doing this is CISA has many members who are trying to make smart decisions. And they said, hey, what's the market of the future going to look like? And we knew that the modeling tools at the time didn't look across days. And when you look across days, you know that your storage can get depleted. And so you'll have to have come into a 3 hot day period or a 3 cloudy day period with more storage. And what this shows is that as we push towards our climate goals in California, we're going to need huge amounts of long duration storage too. And that has led all of us to want to develop the long duration storage toolkit more and more. So what you see in 2045 with the the large blue is 44.4 thousand megawatts of long duration storage, or the total storage. And that pushes even higher to 47.9 as you get towards 2050. And a lot of this is starting to ramp on now. So by 2030, you know, we'll have the 2,000 megawatts and more coming online just of long duration. So I would say this is a pattern that's going to play out everywhere depending on the grid. So if your grid is adding solar and renewables and going to start retiring old fossil units, you're going to start to need first your 4-hour or shorter duration storage, and then pretty quickly your longer duration diurnal shifting storage. And then the whole next question that Omar teed up is, at what point do you invest in seasonal or multi-day storage? Omar, you know, we should coordinate, because in California, we're starting to use a simple definition of seasonal storage is called more than 7 days. And, you know, so that's more than 100 hours, 164 hours. And so if we should all get on the same page so everyone in the world can try to use our lessons learned, and we do all of our modeling in a disciplined way. So anyway, I would say what we're seeing is just one of these rare moments in industry where there's huge demand. The market opportunity is truly gigantic. There's opportunities for everyone, but it is a bit like the Wild West. And, you know, for those of you who don't know, I live in California near one of the areas of the California Gold Rush. And I work in policy and trade association work. So we're the voice of storage. We do studies. I'm never working for a company where we may strike it rich. And so the joke I always use with the companies I work with is that they're the gold prospectors. They get off the boat and I sell them a pickaxe and jeans, and then they go off in the hills to try and strike it rich, you know, and hopefully they do. And I'll never strike it rich, though. I'm just selling pickaxes and jeans. So it is like a gold rush here again. And I think, you know, we're doing it responsibly, but there is a lot of opportunity here, and I hope everybody can get involved. Just building on what Omar said nationally, you know, I'd say, and Omar, we do cite some of your work here, I think. So there's just a huge opportunity. And so everyone needs to figure out how to do this. And Omar, that's why I'm so interested in using standardized definitions, because I think as California and you and others kind of pioneer this, it'll be really easier if everyone can wrap their head around it and we build the language and standardize the toolkits and the modeling. And then for us in CISA, the way we approach it is you have high renewable portfolios, you green up your grid, and then you start to have fossil fuel retirements, which really starts to mean you need more storage. And we're actually seeing that around the entire Western United States now, including in coal states where fossil plants are being stressed and looking to retire. So CISA has actually historically been the California Energy Storage Alliance, but we're now moving more towards an additional offering called the Western Energy Storage Task Force, because once the market is ready for storage, you really need to be involved and have a voice, and that's what CISA does. And so we're now doing this West thing, which I hope you like the name, the Western Energy Storage Task Force. And that's launching soon. So coming to a state near you, I would say, is more storage advocacy, and we look forward to working with everybody. Here's just more about the West. And so that's a bit about CISA. And I'd really prefer, Carlos, if we can, we get to Q&A and let's have some fun dialoguing about it, because big opportunities. Omar's got the technical details, and I can talk about any policy questions people have.
Brilliant. Yeah, I think that's a good idea. We have about 15 minutes to answer questions, so let's get right to it. So let's start with the first question. Actually, I think it's for Omar. It says, in your analysis, how much daily and weekly could be required? By the way, Alex, we can still see your screen. So.
Okay, there we go.
Okay, yeah, that's all right.
That is I will say it depends on the power system, but I am not sure if I am able to share something. Let me share the presentation, because it could be important for people to understand that this is going to depend on many factors, right? Like if you take a look at CAISO, for example, I would say that long duration based on the assumptions and the model, whatever, could take more than 50% of the total market. In MISO, for example, you have a situation in which for 100% renewable energy mix, seasonal storage could take more than or around 50% of the total energy storage market for 100% renewable energy mix. So I would say, the potential deployment is going to depend on the specific power system and also the specific penetration. Regarding the duration, for short duration, I would say between 1.4 hours and 5.1 hours. And then long duration between, I would say, maybe 6.5 hours and maybe up to 15 hours. And then seasonal was between 3 days and 1 month or 1 month and a half, something like that.
All right. Thank you. Thank you very much. So maybe let's go to another technical question. And someone asks, Benjamin Valley asks, what's the best source of data for assessing volatility to understand which substation to connect to? Is that something that you know here? Like, is that to that level of granularity?
Yeah, can you repeat the question, please?
So what's the best source of data for assessing volatility to understand which substation to connect to?
Yeah, I think the current market, right, like current electricity market, I would say the best way is to look at the locational marginal prices that, I think every ISO has that information available. So that, I think energy storage is more about variability, right? It's not about high prices or low prices for electricity. It's more about the difference between the high and the lower prices. So I think the best way is to look at each ISO for nodal LMP data and check nodes with very high variability of those LMPs for a given year. And then you're going to figure out, okay, this location, energy arbitrage or, transmission congestion or whatever is going to be important because you have very high variability of these LMPs.
And I would add, it's really market specific and compensation model specific. If you're looking in Texas, which we would call a fully merchant market, yeah, you're going to be paying for yourself based on your ability to earn market money in the market. And so you're looking for arbitrage or you're looking to sell regulation. If you come to California, a slightly different model, you'll get two payment streams. One would be your capacity payment stream, which is probably more important. And so you'd really be focused more on the capacity side and anchoring your project with a long-term contract. And then any money you get through the energy market is important, but perhaps less so and less critical. And in California, we're also seeing how, and this is very predictable, how the storage can quickly saturate the regulation and ancillary service markets. That happens because those markets are relatively small, but then your peaking market's bigger, and then your diurnal shifting market's even bigger. And so we're seeing the energy markets signal and respond to the storage as it gets added, and these markets get filled up, and then you have to shift to the next market. So I'd say it's pretty complicated, but starting with LMP data and a very clear understanding of who the buyer is and how they would contract is the first step.
Great. Thank you, Alex. And there is a question here, which I think is more markets based, and he's asking, is Ryan Chudgar asks, while the development needs make sense, how likely is this to happen given the material shortages and the higher cost of batteries that we have seen over the last 6 months? So he quotes 30% cost increase. So, what are your, Alex, what are your members saying about this? So what's going on in the market now?
Yeah, so this is a big issue. And over the last 6 months, globally, we have seen, major supply disruptions and project execution challenges in a couple ways. I previously was calling them the 4 horsemen of the apocalypse, but I was told that that's too scary. So you're seeing commodity price changes that are very material. And in my world, working with all these companies, many of them have upstream minerals processing and mineral supply agreements for manufacturing batteries. So this, and even those upstream contracts have been broken, and we're seeing dramatic price spikes at the upstream side of the supply chain. And so then everybody's trying to pass along those cost increases and line up the supply. So that's been quite significant. And in the world of lithium-ion batteries, the price increases we've seen in lithium carbonate, some of the source materials like lithium carbonate or copper or electrolyte, have clearly upset the project economics, and they've taken profitable projects and made them unprofitable. And so obviously that's a problem, because no investor is going to finance a project that's guaranteed to lose money. And so it's prompted us to have a bunch of discussion about what is the impact of the supply chain and how do we address that. And the first thing you do is you allow pricing adjustments in contracts, which is complicated but doable. And then on a go forward, what you do is you start to embed commodity risk in the contract, and you have commodity floating provisions in contracts. And a good example is, and this is where our industry is maturing. If Carlos, if you wanted to hedge your risks on oil prices, there are 15 indices that everybody knows. A good example in the United States is the Henry Hub oil price, and you have forward contracts or spot markets. But if you were to try and hedge your commodity risk for lithium carbonate, there is no standard index yet. The two closest indices we have is the London Metals Exchange and the Shanghai Metals Market. And even those are spot markets. There's no forward market to hedge against yet. So it's a perfect example of where our industry is maturing. And even though it's obvious we should have had a forward market to hedge against lithium, it was still a boutique market. And now that we have electric vehicle batteries and everybody's interested in the price of lithium over the next 10 years, we will have these hedgeable indices established. But it's just something that was hard to do in the beginning, and it's prompted us to have these challenges. Additionally, and everybody knows, the supply chain challenges emerging from China, particularly as they lock down close to 400 million people, were significant. And for California, we've been ordering batteries and equipment that were sitting at the ports and unable to be exported because there was no one able to work at the ports or load the ships. And so those have been challenges that are just disrupted the market. And I would say we're starting to work through the supply chain issues. We're maturing on the commodity risk and overall commodity contracting issues. And then on our side in California also, and I think this will happen everywhere, when you add so much storage and renewables to the grid, you have to modernize your electric grid. And that is challenging too. And you need a lot of engineers, and you need experts, and the utilities or the grid managers have to plan all of that. It takes a long time. And so you want to get ahead of that challenge. And I'd say even though it was predictable, the systems we have in California were not equipped for the scale of change. And the scale, imagine normally you deal with 10 to 15 projects a year, and suddenly you're dealing with 100 to 150. Your systems will need to modernize. So in all of those frontiers, we've been dealing with these challenges. I would say the one great piece of news is that the US at the federal level had some federal tariff rules on solar that were also very disruptive to the solar supply chain. I think they were well-intended rules, but the execution and the devil's in the details. And in this case, the solar rules were actually going to dramatically disrupt solar development for the next couple of years, including risking reliability impacts. And so just this week, they've announced they're going to unwind those rules. And I don't know too many details yet, but that's a nice outcome in terms of near-term help for the industry. Yeah.
So, well, thank you for the answer, Alex. Very comprehensive. We have, a few minutes left. There are quite a lot of questions actually that are related to the assumptions in the forecast that Omar has presented. Omar, maybe I know that you guys at Enroll normally publish these in reports. If you have a link to the report, actually, maybe you can put it in the chat function. And I think once you put the link in the chat, people can check it and see if the questions have been answered. But they're all valid questions. But there are a few, like 3 questions I think related to technologies that are related to other to other things other than lithium ion. So Pearson guest asks about flow batteries and whether flywheel technologies could be used for black start function. And I think these questions are valid because of the challenges we've been talking about regarding supply chain and material availability. What are your thoughts on these, Omar, Alex? Are other technologies ready for prime time now?
Yeah, that is a very interesting question, and that was one of the reasons why we use genetic technologies in our analysis, because each technology is going to face constraints. For example, lithium-ion batteries, then you have problem with critical materials, right? As Alex was mentioning. If you are trying to develop pumped hydro energy storage, then you don't have locations to deploy that technology everywhere, for example. Or compressed air energy storage or hydrogen energy storage, you cannot deploy those technologies everywhere because you need the underground storage facility, right? Like, you need those properties that you cannot find everywhere to deploy those technologies. So I would say in general, right, we are going to need a diverse portfolio of technologies, including, flow batteries, different chemistries, etc. And the key message here is that you should avoid any constraint your supply chain, because in that way you can scale up production, because I think we are going to need massive amount of storage if we want to achieve higher penetrations of wind and solar PV power sources in the electricity system. So I will say, any technology could be useful. You need just to define your market, for example, the specific constraint that you may have in your supply chain system, to make sure that you can scale up that solution. If you are not using a material that may be critical, and then when the system is going to need your technology, you are not going to be able to produce that technology at the scale because you have some supply constraint, and that could be a big issue. So in general, I would say we are going to need a variety of technologies, because we need a variety of services that to support the grid with high penetrations of wind and solar PV power sources.
Yeah, if I could, I would add, I break the problem in as follows. I say, are you a modular commercial technology that scales? Because if you are, then we take you on this path, and you basically say, build a 500 kilowatt pilot, then build a 1 to 2 megawatt project, then build a 5 to 10 megawatt project. And each time you do that, you expand your manufacturing, you tune your manufacturing, you improve your source efficiencies, and you get up to a scale where you can do 50 megawatt projects, which to me is sort of prime time for utility scale. And along the way, the insurance and financing communities understand how you operate, and everybody gets better. So if you're a scalable modular, we take you on that path. If you are a very large site-specific or infrastructure type solution, a good example of that would be pump hydro, or a company I work with, HydroStore, HighView, really large projects that are can be modular, but still are so big that you don't really start small. You don't do 1 megawatt with those sizes of technologies. And so for those, you take a slightly different path, and you say, okay, we're going to do what's called a buy down approach. Maybe use tax policy or infrastructure style spending to build these things. And then you get large chunks of new capacity installed. So you have to decide, how are we going to do that? And in the end, you need probably both paths. And I think just looking at the numbers Omar shared, just gigawatts of storage. I mean, this is gigantic. Imagine we were just starting to build all of the freeways in the United States, right? It's sort of that level of market expansion and launch. And so you're really at a point where it makes sense to figure it out, and then you're going to start spending the money, because we're going to be doing this for 2-3 decades, and we want to be as efficient as possible. And so I'm very excited about the Department of Energy funding and the work in California with their Energy Commission in the budget for another close to $400 million, including some money for hydrogen, really get this started and really make sure everybody's organized and we've got the toolkit and the paths designed. And then, hopefully the markets can take over and get everything built efficiently.
Thank you very much, Alex, Omar. I think, it's time for us to move to the next session, but it's been great. Please stay on. You can just switch off your cameras, and if you want to, you can even answer the few questions that are left there on the Q&A box. And yeah, well, thank you very much. Please stay on with us, and yeah, you can answer questions, ask questions, and everything.
Thank you very much, Carlos.
Thanks for having us, Carlos. Appreciate it. Omar, great job. See you soon. Okay.
Thank you, Alex.
Cheers. So I'm just going to share my screen again so you can see the next session coming up. So in the next session, we'll have Michael Carpel from Wärtsilä and Sharif Abdel Sarak from Duke. This is not the one talking about designing, building, and operating utility-scale hybrid solar or wind battery projects or standalone. So how are you today, Michael, Sharif?
Doing good. Thank you, sir.
Great.
Doing great. Hello, everyone.
Hello. So, well, Michael, Sharif, welcome to this session. So, I think for those who have joined late, I'd like to remind you that yes, we're recording the session. We'll send you the recording and the slides, and please do send your questions through the Q&A box. Good to see people interacting in the chat as well. So. Could you, Sharif, please introduce yourself briefly before we start with the presentations?
Absolutely. First of all, thanks for having me. So this is Sharif Abdulrazak, Director of Renewables Engineering for Duke Energy's team that is focused on the design, development, and execution of energy storage and microgrid projects, both in our regulated footprint, which is North Carolina, South Carolina, Indiana, Ohio, and Kentucky, and Florida, and as well as kind of nationwide through Duke Energy Sustainable Solutions, our commercial arm.
Great. Thank you very much, Sharif. And Michael, would you introduce yourself briefly as well, please?
Hi, I'm Michael Carpel. I'm a business development manager here at Wärtsilä. I've been doing renewable energy project and product works for the last 13 years. And I started doing batteries in around the 2015 timeframe. I've been previously with Tesla and Nextracker, and I joined Wärtsilä about 15 months ago. Thanks for having me.
Brilliant. Thank you very much, Michael. So, right, I'm going to stop sharing my screen now. And I am not sure, actually, which one of you is supposed to present first. So it's going to...
That would be me.
All right. Sharif, please go ahead and present.
All right, very well.
And
do let me know once you're able to see my screen.
I can see your screen perfectly. So over to you.
Okay, great. Again, my name is Sharif Abdulrazak. I head up the team that focuses on the development and design of energy storage projects within Duke Energy. Today, we'll be discussing the capability and potential of energy storage to be the key to unlocking carbon neutrality for our utility. So just a brief intro to Duke Energy. We've been in service for 150 years, 8.2 million electrical customers, 1.6 million natural gas customers in our regulated footprint. We're a Fortune 150 company and own more than 50 gigawatts of generation capacity. If you're within the Duke Energy kind of bigger family, you have probably close to 40,000 employees, you're going to be very aware of our carbon reduction goals. We're all working in sync to achieve it, and it's very likely you've participated in or provided input for the plan to achieve that carbon reduction goal. So we have basically two goals. One, reaching 70% carbon reduction by 2030, and that's compared to our 2005 carbon footprint, and reaching net neutrality by 2050. So right now we're tracking well towards that. 2021, we're at 41 million of short tons of carbon compared to 76 back in 2005. And we've, you may be familiar with our Carolinas carbon plan that we've recently published to our regulators. We developed in that plan a very detailed generation resource list for how we're going to get there, how many coal plants we're decommissioning, new solar facilities, offshore wind. Some options have nuclear, but if you look at all the generation mixes here from P1 down to P4, you'll notice that there's a focus on battery storage. The one with the least battery storage in there is P4, where we're heavily leveraging offshore wind and nuclear as well. So what does this mean for our team, for our energy storage team within Duke Energy, is that at the very least by 2035, we will need to have 2 gigawatts of energy storage installed and operating, and at the most 4.2 gigawatts if we're going with the P1 strategy. So in these slides, we're kind of going to focus on how we're getting there, some of the challenges we faced in the past and how we've overcome them. And the hope is that these would be kind of lessons learned for kind of the audience and for others to leverage. So starting off, when we kind of started the energy storage program within Duke Energy a couple of years ago, probably around 2017, one of the biggest challenges was, all right, where do we put them, right? You have a very versatile, very flexible tool that can do a multitude of things, whether with its active power capability or reactive power capability. And because it's inverter based, you can obviously dispatch it really fast, which makes it even more versatile than your typical generator. So how do you take a tool like that and find the best locations on the grid where it's needed the most? So we developed a couple of strategies. I'm going to focus here on the reliability application. So how do we find the locations on our grid where energy storage systems can uniquely meet or improve reliability for our customers, where and are also more cost effective than wires alternatives? So we've kind of addressed it a number of ways in the beginning, involving kind of working with subject matter experts in our distribution planning teams, transmission planning, and other groups. In the end, we got a lot of lessons learned and developed a identification method that we've kind of grew, and it represents now a source of our pipeline of projects in our service territory. So one of these methods is the AR index for identifying projects. So what this involves is basically, if you have a feeder, you look at each and every single node within that feeder, and you deduce two main values for it. one, distance from the substation to that node in miles, and two, power capacity of load downstream of that node. So for example, if you're looking at, this node B, look at the distance of this node from the substation and the capacity downstream of this node to the end of the feeder, you deduce this value called M, which would be in MVA miles. So what does that represent? If you think about it, it would represent basically nodes, or the higher the number is, the more the load that is distant from the substation. So more load away from the substation, which means these are the load pockets that are going to be most susceptible to outages. So that's going to be able to identify for us radial feeders that have load pockets that are impacted more heavily from outages, because every outage or fault upstream, these guys get affected. So what we did is, we calculated that for each node within our feeders. We take the maximum M value for each feeder, and we basically prioritize our feeder to see where our most disadvantaged customers are. So that was the method we deployed or used for identifying the Hot Springs project, which is a 4.4 megawatt hour project in Western North Carolina with a 2 megawatt solar facility. Our good friend Michael is helping us with that project still with Wärtsilä, obviously. So it's definitely a great story to, for energy storage, because the wires solution for this project was just prohibitively expensive. You have a very long 11-mile distribution feeder going through kind of mountainous terrain in Western North Carolina. Getting that underground to improve reliability is, of course, cost prohibitive. So economics actually worked out for the microgrid solution, so which is here, and this is kind of the town that it serves. So another kind of challenge I wanted to stress on kind of relates to the difficulty of modeling project cost due to the high dependency on BESS degradation. And to elaborate there, so we have two main issues here. One, the cost of battery cells. If you look at the overall project cost, the cost of the cells represent approximately 40% or a bit more of the project. And two, the beginning of life capacity, which means the actual number of cells, number of battery racks, highly depends on the degradation of the cells, or the expected degradation of the cells over their lifetime, which in turn depends on the use case that you're going to use that system for. So the issue we have when we put these two together, coupled with the lack of modeling tools that would be able to deduce your degradation for certain use cases, makes it difficult to identify the cost of a project, at least accurately, because you can't find the expected degradation on the front end. So what do you do as an engineer when you have uncertainty on any parameter? You become conservative. So what we were finding is that we're becoming more conservative, because obviously you don't want to end up with a dead battery before end of project life. But so what we were finding was that we're costing ourselves out. So it became apparent that we need some new tools, new methodologies to be able to simulate degradation, model degradation for different use cases. So we started kind of looking at the software tools out there. A while ago, we leveraged one of them called Storalytics Energy Storage. It helped us kind of model very accurately these battery systems. It's kind of in a way similar to PV-Syst, where you have a battery model kind of similar to PV-Syst.ond files, have an inverter model, and also you input your project profile, which represents the use case. So leveraging these inputs and that tool, we're able to accurately deduce degradation for different use cases like reliability, peak load shaving, regulation, and just through that analysis, identify what would be the cost of the system if we're executing this use case versus another, which allowed us to eventually optimize both use case and battery technology and product. So these are some of the results that we've gotten through some of our analyses. So for this curve, it was basically just a peak load shaving application only. We've, over 10 years, we're able to get just 8% loss of state of health. Of course, this was just one application. Part of the design process involves stacking different applications. So once we did this, we kind of stacked another application and found kind of what would be the additional degradation there. And then you're able to kind of calculate the incremental cost per added application and per dispatched kilowatt hour. Other metrics included kind of identifying the adequacy of the design system to meet the requirements of the use case, which isn't always straightforward, especially on the energy side of things. So for the power capacity here, things are pretty straightforward, but with energy, you want to make sure that you're getting the full POI discharged energy and POI charged energy that's needed by your application. In addition to that, kind of finding the details of round trip efficiency for lithium and other technologies to be able to also compare different technologies, different batteries, and even lithium subchemistries side by side. And that is it for my slides. I'll hand it back to you, Carlos.
Thank you very much, Sharif, for your presentation. So I think now we'll jump, straight into Michael's presentation. So Michael, whenever you are ready, just start sharing your screen and start presenting. And I'd like to remind everyone in the audience that you can send questions. So send them through the Q&A box, and we'll get to them at the after Michael finishes his presentation. So, well, without any further delay, over to you, Michael.
Great. Thank you so much. Thanks, Sharif, for that opening. I'm assuming everyone can see everything okay. Please let me know if that's not the case. So, so this panel, I'm going to go relatively quickly through some of these slides. I think a lot of you are familiar with Wärtsilä. We're a top 3 integrator in the energy storage space in terms of deployments, and our greater Wärtsilä energy team. We just have a ton of experience globally. We're in 180 countries. We have many gigawatts of power plants in operation and under service contracts. And so our footprint and lessons learned in deploying energy projects across the globe is very high. In terms of energy storage specifically, we've really installed under every use case there is at this point in pretty much every region. And there's a lot of lessons learned there that we're applying to be able to guide some of you today. About 2.5 gigawatts of energy storage and about 4.5 gigawatt hours. But This specific webinar has some specific questions I want to answer. I know everyone read the prompts and everyone knows exactly the questions on this webinar here, but a few I'd like to hone in on is understanding one of the key drivers to success in energy storage is revenue. How are financiers want to know how they're going to make their money, and specifically how EMS, the energy management system, helps with that. So at Wärtsilä, we have GEMS, which is our EMS. And when I talk to people about EMS, which is probably every other day, depending on what your role is in the industry, you may see EMS differently than another person. And so I like to break down EMS into a couple of different functions. The first is sort of like on-site controls and plant health, right? So this is making sure your batteries are balanced for maximum state of health and that everything's working safely, and that if you're going through an O&M cycle, that you can control and shut down specific portions of your plant while the rest of it can still be run, things like that. How much cycling have you been doing? Then there's some remote in EMS cloud functions, which is a little bit tied into what I just said, but this has a lot to do with being able to optimize, especially when you get to a fleet level of plants, remotely being able to sort of pull the puppet strings to be able to maximize your fleet of assets. And then the third piece of it is the revenue side of the whole business, which is nice and complicated in the US, as every market is quite different, but being able to have primary value streams anchoring out value streams, and you know, sort of the cherry on top merchant revenue streams, and also being able to adapt to revenue streams as they change. And so you know, our GEM system is really powerful at all of those different pieces of it, but I'd like to just hone in a little bit here on the revenue side of things. So getting successful value stacking is going to be very, very important. You're going to want to be able to have your plants programmed with almost like a hierarchy of decision logic. There are traders that want to be able to manually optimize their bids, particularly in merchant markets. But for the most part, you're going to want to have some set points to be able to optimize this without, you know, as much human error. And that's what your energy management systems can do for you. So here's a case of a CAISO project where there's a lot of arbitrage opportunities, but there's also several ancillary service opportunities. And what's really important is not specifically how this project is making money, but it's that process of being able to stack rank how you want your plant to operate. And if we look back at the previous session, Alex Morris made a really good point out. Some of these markets saturate really, really quickly. So it's not like you can set up a hybrid solar and storage plant and have one plan and that's just how it operates for the life of the system. You're going to constantly want to be able to optimize where's the market today, what are my locational marginal prices today, what projects are coming online in my area, and how could that possibly affect my revenue streams, and being able to switch your strategies over time is a really key element to that. So how do you do that? Well, there's the operational aspects of it, which I've already talked about, but there's also the testing of the strategies. And so that's where a lot of the cloud functions of EMS can be very important in terms of having almost like a sandbox to be able to backcast or back test strategies, or to be able to project forward strategies. So whether you have your own in-house forecasts of either energy or pricing, or you have historical data that you want to test against, or some sort of combination, you can sort of build a world to test different strategies and compare. If I had done this, what would have happened? If I were to do this, what could happen? And constantly being able to optimize that. And and so again, EMS, sort of a broad umbrella topic for software in general, but there's a lot of different important pieces to it. I think a third aspect of that is what's the opportunity cost of using my battery? If you're using a technology such as lithium that degrades, you may want to understand what is the state of health, the sort of mileage trade-off between cycling this battery more versus the revenue. The first cycles are going to be probably the most valuable in your strategy, and it's going to be a no-brainer to cycle it. But as you cycle more and more, there may be a point where it's not worth the opportunity cost of doing that. And so having reports for that trade-off can really, really help as well. Another piece of our topic today, how to design, build, and operate profitable utility plants, is a couple different things. Let's talk about safety for a second. Safety is one of those bars where it's a must meet, right? If we can't build these things safely, the whole industry's in jeopardy. So that's extremely important. But when we start digging into the nuances of safety in the context of building and operating plants profitably, it's important to understand what is going to be expected of you in your project. And so we really have two challenges in my mind when it comes to safety. The first is that standards are evolving. That's actually kind of the easy part. And there's plenty of really smart engineers that are much smarter than me that are figuring out how to best manage those standards in the testing and the safety. But the second piece of it is a little bit more complicated, and that's how those safety standards are interpreted. And there's a lot of leeway there. So, the challenge with the US is we have federal, state, and local bodies that can interpret these differently. A fire marshal in ABC County may interpret it differently than in XYZ County, right? And that's even within a single state. And so being able to get ahead of safety standards and speak to those people ahead of time so you can properly budget in your costs is something that's very much going to help you. That's just the AHJ side. I would argue you have the same pieces for insurance as well as financiers. Energy storage is relatively new compared to, say, solar, and a lot of these financiers may be coming from that world or other similar energy worlds that are not energy storage and may not fully understand all the aspects of safety that may affect their project. And so what you don't want to see is a large scale deployment get really far down the road and then get hung up over something that you thought was relatively minor. And so in terms of talking about safety, Wärtsilä, we've designed our systems to have a great menu of options to be able to accommodate any of the potential safety issues that you may run into, everything from how we're selecting the cells to how we comply with the safety standards that are out there, having modular designs to be able to isolate any thermal events that could happen, all the way up to detection, suppression, and monitoring. For the sake of time, I won't go into every detail there, but just wanted to paint the context of safety in terms of making profitable plants. And then finally, just in terms of how we can possibly get these plants built on time, because I think, again, if you go back to the previous session and you look at what Alex Morris said at CISA, I forget exactly what he said. It was something like, the California is set to deploy the same amount of storage as LA 3 times over in the next several years. I mean, we've gone from when I started doing energy storage in the mid-teens of the century, like pretty small projects, pretty boutique, to now where we really have this rubber meeting the road scale. That's going to create a lot of growing pains, or rather we are feeling a lot of growing pains. So a lot of what we've done to try to optimize cost and price and be able to deploy these is, building these modular systems that are standardized Everything was a science project, half a decade ago, and being able to optimize things like logistics that have gone completely out of control since call it 2019, and to be able to manage the supply chain as best as possible. So with that, I'll leave it there. We'd love to keep time for questions and whatnot. I just have a few case studies here that talk about our ability to be able to balance those revenue streams going back to the EMS side of things. Here's an example of a DC coupled large scale solar and storage plant where there's both incentives and penalties and complicated PPA structures that you're trying to optimize that could shift over time. And that's where having a really strong EMS can help you. Same thing with merchant markets, like in ERCOT. You're going to constantly be testing strategies as saturation levels on your node change, as the resource mix changes, and then things like extreme weather driving price spikes in a fully merchant market. That's it for my presentation. Looking forward to the Q&A.
Brilliant. Thank you very much, Michael, for your presentation. And yes, we do have a few questions here in the Q&A. Let's get started with the first one, which Sharif has just mentioned that he would like to answer. A question by Manda Hodegaoka. Please, Manda, sorry about my pronunciation of your name. It says, also, how do you address change in RTE on an annual basis?
Yeah, it's a very good question because, obviously, round trip efficiency and specifically in the lithium battery system depends on internal resistance of cells, which tends to increase the more the cells degrade. So the internal resistance at later years is definitely expected to be different from prior years. To answer that question, in this tool, there's an option to set the starting state of health of the simulation, which you can correspond to the year you're trying to simulate, and that way it would produce the expected round trip efficiency values with the level of degradation associated with that specific year in question. I hope that helps.
Brilliant. Thank you very much, Sharif. Let's answer the question by Steve Ivy, who asks, do you have any, have any of you thought of EPP or MPP systems in terms of service life? EPP systems in particular should have an extremely long useful service life.
I'm sorry, what are we referring to when we say EPB?
So I think EPP means external battery packs, I believe. MPP, I'm not sure what it is, so I was actually hoping that you would know. If we're not sure, we can go to the next question. So
yeah, I'm not sure what external battery packs is referring to.
Okay, so he's talking about his earth pressurized bladder or monolith pressurized piston systems. He's talking anything about different technologies other than batteries.
I'm an electrical engineer, so
I mean, look, I think that there's a place for a lot of different technologies, right? A lot of our focus comes around lithium because we're at the rubber meets the road phase right now. And for example, in California, if we don't succeed at deploying, we're going to have blackouts in the summer, right? So there's a level of short-term focus right now on dominant technologies. But, I think the whole last panel talked a ton about long duration energy storages, medium duration energy storages, the definitions around that. I'm not an expert on the technology that you're talking about. Sharif's looked at a lot of different technologies, and we would welcome a discussion on how you evaluate non-dominant technologies and technologies of the future, but I can't specifically speak to that technology. My non-lithium experience is much more focused on flow batteries, flywheels, looking at gravity type systems, things like that.
So, just taking a step back, to a more general questions of what do you think is required for utility scale energy storage to grow? What's needed? right now?
Man, that's such a loaded question, but and there's definitely a lot of things. But if I had to select the highest priority, in my mind, it would have to be development of industry standards and tools, basically to address that very last question. How do you compare new technologies to each other? Obviously, parameter-based characterization, which is just, yeah, this technology has a depth of discharge of this much and a round trip efficiency of this much and a self-discharge of this much per month. That is not meeting the needs, of our industry. I believe there could be a lot of value in use case profile standardization and accordingly development of technology specific scorecards that are based on these standardized use cases. So that way, we'd be asking the right question, which is, what is the most suitable technology for this application, instead of asking kind of the much more, in my opinion, misleading question, which is, what's the best energy storage technology out there? I see, that being said, I see a lot of promise in new technologies like EOS and Venue. There's a lot of gravity technologies, a lot of new flow technologies. I think we'll be better positioned to unlock their potential by clarifying where their edges are over lithium or another base case.
Yeah, and to add to that, I always like hearing the utility answers from the utility themselves. So thank you, Sharif. From where I sit, the biggest challenge in the industry is this price volatility. I think logistics has put a lot of pressure on us, but Sharif was talking about how lithium batteries comprise 40% of the system cost or so. So having volatility in like a major chunk of the price makes it even harder, to the point where it's not like, hey, let's just negotiate, just absorb that industry. The margins in this industry aren't large enough to absorb some of those price swings. And so I think a major barrier that, again, the previous session alluded to is trying to figure out how off-takers can have some sort of indexation for portions of it, and be able to absorb some of that risk. I know particularly utilities have decades and decades of experience on firm fixed contracts, and as generally the gorilla in the room, you want to throw that weight around. But if we really want to deploy energy storage systems successfully and keep gaining this incremental experience and lessons learned, we need to keep deploying projects. And those kind of sort of flexible offtake structures are going to be really needed for success, at least in the short term.
So, I think a question I have, and I think it's a question that would speak to a lot of the people who are with us today, is how do you assess some of these new technologies? So it seems, and correct me if I'm wrong, whenever I see people talking about storage, they're really talking about either lithium ion or pumped hydro. So those are the two that the market seems to be comfortable with. But as you mentioned, Michael, there are lots of, and Sharif, there are lots of new technologies that are showing promise. They could, give you a way around some of the challenges that there are in terms of high material costs and, bottlenecks that we're experiencing now. So, how do you actually look at these technologies and assess whether they're suitable for a particular use, whether they could be profitable to run in a specific market?
Mm-hmm. Yeah, I think you hit the nail on the head with the portion of that question when you said a specific use. That's the starting point. So kind of as we alluded to earlier, you should always start with the use case. What exactly do you need? So just as a high level example, you may look at a technology with, like, for example, lead acid, or just a technology with suboptimal round trip efficiency, really shouldn't be negatively looked at if the application it's needed for is a low cycle count application. So, like, case in point, for instance, is with UPS systems, right? A lot of UPS systems out there use lead acid. You know why? Because lead acid is just great at storing energy. And when I say that, I mean the self-discharge is very, very low. And probably one of the major drawbacks for lead acid is just round trip efficiency and some maintenance requirements. But for an application like UPS, where you're really only cycling a number of times a year, you really don't need to look much into that round trip efficiency feature. So that's what I mean when I say, just don't look at the general scorecard of the application or of the technology. Look at it with the use case in mind to find what's most suitable for your application.
Yeah. When you're evaluating other technologies, I sort of see three aspects of it. The first is, are there any niches that the dominant technology today definitely shouldn't be used for? One example for that is I saw some non-flammable technology. I want to say it was a compressed air type technology, because it was in like a super remote mountain fire station that like barely even had a road to get there, right? Or like really urban areas where you really can't have a thermal event, right? So there's going to be technologies that will just fit specific places. Another one might be, emergency power, moving, I don't know, like basically a semi truck with a bunch of energy on it to some sort of first responder situation, right? Those niches. But once we start really getting into the mainstream, the scale that I think most of us here are interested in our organizations, there's the revenue and technical characteristics. So that's what Sharif was talking about. He's the expert on looking at RTE and modeling it versus use cases. You can come into a strong EMS and be able to like tie those characteristics into predicting what your revenue is, but there's that whole aspect of it. I think the third piece of evaluating non-dominant technologies that I'd rather focus on is talking about their track record. So at the end of the day, what do we need? We need billions, maybe even trillions of dollars invested into this space. And typically investors and insurers aren't going to invest in something where they just really don't have subjective raw data operating history to be able to do. And so being able to get those 500 kilowatt and then 1 to 2 megawatt and then 5 to 10 megawatt pilot projects in succession to show operating history, to help hone in on manufacturing improvements that can be made and to ultimately get to that scale. No one wants to be the first person to jump on a technology, but if we never invest in these technologies, by the time we need it in, late 2030, 2035, 2045, whenever it is, we're not going to have it. So we really, really need that operating history now. And that's why there's one, forward-looking groups that will invest in pilot technologies. Two, there are grants associated out there. I think in California, for example, there's the CEC grants. The California Energy Commission has some grants out there for projects like that. But if you talk to financiers and insurers, they just don't touch it if they don't know what it's going to do. And so that's probably the biggest barrier to getting some of these less dominant technologies up and running.
Right. So, well, it sounds like, we have some of these technologies, they have a long road ahead because they need to build this track record, but also to do so quickly. So, they can be ready to be deployed when required. And everyone keeps on talking about 2050 as a target. And, you might argue that 2050 is really far away, but it's actually not that far away, So it's within well, fingers crossed, within our lifetime. So if we can see to see net zero, we'll definitely have to see some of those other technologies. But bringing it back to the short term, so what do you think we can see in the next 12 months in the industry? So what do you expect is going to happen in the energy storage market in the US in the next 12 months? Sharif, I don't know if you'd like to, or Michael, whoever wants to go first.
Sure, I can just take a stab at that from my perspective. I think we're going to be seeing a lot of pilots, a lot of demonstrations for just new technologies out there. It seems like for the past year or so, every couple of weeks, you kind of hear a news release for kind of a new technology, and every one of them is just more exciting than the other. So I'm really interested to see kind of how these pilots will perform, what kind of use cases will be determined as the silver bullet for each technology. And in my role with Duke Energy, kind of finding the best location on our grid to make the best use of them. So looking forward to it.
Yeah, and so 12 months, 5-6 months ago, my answer over the next 12 months might have been similar but slightly different. I think the major industry changes with indexation and the auction tariff implications have really changed the trajectory of the next 12 months. It sounds like the auction tariff on the solar piece of it. So for those that don't know, the auction tariff was a trade case that basically put hold on modules being imported into the US for various reasons. And there's a very, very strong supply shortage for solar, basically creating uncertainty and pushing out commercial operation dates for solar plants, which, as we know, are increasingly paired with energy storage. So I'd say the next 12 months has probably cooled off a little bit, because even if there's some relief there with some of the recent Biden administration certainty around the 2-year exemption that was just released, I think, a couple days ago, you've probably still seen a lot of those projects push out. With that said, we're still at an unprecedented scale in terms of deployment. So what are the next 12 months going to be? A lot of growing pains, a lot of AHJs seeing safety requirements for the first time and interpreting them, a lot of hopefully not supply chain start and stops, but I think we're going to go through a lot of growing pains, and we're going to need to come out the other side with some sort of consistency in safety interpretations so that there's predictability for developers and IPPs and operators. And then we're also going to need, like I've been harping on this whole webinar, some sort of way to share the volatility in the market. So there's going to be some contractual evolutions with these deployments.
So, well, as they say, never a dull day in the office. I think for at least 2 years, we've had many a surprise, and not just in the energy space, but I think the energy space has been pretty lively. So there is a question here, actually, which I think is also by Amanda, and I think, just brings things a little bit back down to more on the operational level, but I think it's a good question. And he asks you, Michael, how do you make use of past experience into creating a more optimized EMS? So I think, well,
it's a great
everybody,
question, Mandar.
Everybody who's got a battery, they want to operate it better and better, right? So
yeah, and not take any risk on it. I'm just kidding. Well, there's different levels and different ways to answer the question in terms of using experience to improve EMS. First off, operating history with your own product can help. So if we go back to, and I'm actually going to share my screen again. So if we go back to this slide here, there's a lot of lessons that you can learn about how your equipment operates, especially as we start hitting augmentations, which to this point in the industry, there haven't been a ton of them, but there's going to be a lot of learning there. That'll really help on the optimization side of the EMS. But as we get to this side in terms of bid optimization, this is like a nice little quarter slide here. There's a lot that goes into it. So every time an organization with a strong EMS deploys in a new region, you're going to learn a lot of characteristics about that market. So PJM versus ERCOT versus a lot of the Southeast Power Pool versus CAISO versus MISO, they're all very different, right? And those are just a few exceptions. And so learning how those market mechanics work will always help an EMS to improve. There are aspects of that, though, that won't necessarily be able to look on past experience. So certain locational node attributes that may or may not be super helpful in terms of previous lessons learned. And sorry, I have a toddler and he is having a complete meltdown outside right now, everyone.
I hope he's
trying
right.
to gather my thoughts here. Okay, sorry. And then just the last aspect of EMS in terms of lessons learned is, do you have enough data to start getting those forward-looking forecasting strategies? Some markets are easier to forecast than others. There's multiple kinds of forecasts. There's your energy forecasts. Those are pretty locked in terms of what is your solar plant going to do based on weather, right? And then there's a little bit more challenging forecasts. If you talk to the experts who forecast CAISO prices, they will tell you it is very challenging, right? So I think that over time, we will learn a lot about being able to forecast revenue. And depending on the market, that's extremely challenging right now. And part of that is just, the ramp curve in terms of proportion of every new project. We're on a steep curve of adding storage, and in shallow markets, it's like a market can be like great one year and disappear with just one or two projects. So as we move down this longer time scale and we start having a lot more predictable applications like shifting and capacity, then I think the revenue models will be a little bit more predictable.
Thank you very much, Michael, for your answer. There is a question here actually came through, not through the Q&A box, through the chat, but I think it's a good question, so I'm going to make an exception of it and answer it, even though it wasn't sent through the Q&A box. But this person is asking, with the majority of US coal power plants retiring by 2030, how do you see the capacity market of utilities filling in the generation deficit outside of renewables plus energy storage? So I think that's the first part of a question, and I think that's a question in itself. Then he goes on to ask what technologies are best positioned to capitalize beyond lithium ion. But yeah, what are your thoughts, Sherif, on these questions?
Sure. So I'll answer through kind of our Duke Energy's carbon plan that, like I said, targets reducing to 70% of our 2005 levels by 2030 and net neutrality by 2050. So to get, just taking a screenshot of, the different scenarios, with that plan in mind, by 2035, in most of the scenarios, we're leveraging solar a lot. We're leveraging onshore wind and offshore wind. I would say the lion's share for us is mostly solar in a couple of scenarios. When we do leverage offshore wind, it becomes the lion's share. So there's I think a lot of possibilities there, and I think it's always good to have a plan B as we all recognize how fast technologies change, and that's why I think we came out with not just one plan that will have this much solar, this much wind, this much onshore wind, this much nuclear. We came out with a number of them. Being frank, for the other part of that question, how much energy storage, non-lithium energy storage, would I expect to be in there? It's really, really tough to say, because I think the technology market is extremely volatile. We're seeing dozens of new technologies every day. For this scale, kind of as Michael alluded to, and as kind of in the prior sessions it was alluded to, for this scale, you're not looking at just brand new startup technologies. You're looking at successful, and I mean very, very successful pilots, because at least for Duke Energy, these are going to be assets that are going to be rate-based and paid for by our ratepayers' hard-earned money. So we'll definitely not kind of venture out with unproven technologies. Today, I would say we're focusing on lithium only. A year from now, I wouldn't be surprised if we added 4 or 5 new technologies to that ready to deploy list.
Yeah, and great job breaking that into a couple of different parts. I think the first part is, how are we going to replace these coal retirements? I think it's fairly simple in some of the easier to reach areas where you already have N+1 or N+2 transmission. That's a lot of the standard development that's going on with solar plus, wind plus, storage type scenarios. I think the challenge, and I don't necessarily have the answer, but the challenge is where you get into some of these really remote pockets, some of these resource adequacy capacity markets where they're very, very isolated. Not to make everything so California centric, but it is where I live. Some of the coastal areas by Santa Barbara or up by like Mendocino are good examples of it's just hard to get resources in there. And so one of the challenges to being able to succeed at helping those areas is getting our modeling right. So a lot of utility models only look at single days. They don't look at what happens in a multi-day, week, 2-week cloudy period, or when the wind doesn't necessarily stop. And they don't necessarily look at, energy storage is a new technology in the sense that it's an energy limited resource. And so I think a lot of the resource adequacy capacity models in the US are evolving to incentivize state of charge under certain conditions and to try to collect more data around making sure the energy is actually there to charge the battery. I mean, you could put a 500 megawatt 4-hour battery near Mendocino, but if you don't have the solar, the wind, or other generation source to power it, it's not going to be very useful. So there's definitely efforts to be able to solve that, and those are the areas that I'm worried about. That does lead us to non-lithium technologies, which is, I think, a great segue and very related. I don't necessarily want to sit here and promote any specific technology, but there are technologies out there that are specifically trying to solve the multi-day reliability type scenarios. There's steady state batteries, kind of like the Form Energies of the world, but there's also, a lot of hydrogen development as well that could solve that kind of piece of it. So it's going to be fun to see a lot of these different technologies, but the charging element of energy storage in these pockets is going to be a lot harder to figure out.
Brilliant. Michael, Sharif, it's time for us to go to the next session. So thank you very much for your presentations. They have been very insightful. Please stay with us and ask questions or answer questions. And yeah, thank you for being with us today.
Thank you, Carlos. Thank you, Michael. Always a pleasure.
Thanks for having me. Thanks for all the great questions, audience.
Brilliant. So, and to everybody else, please do stay with us. So now we are going to the third session. Let me share my screen here so you can see what we'll be talking about. And there we go. So we'll be talking about new revenue streams and innovative business models for lithium-ion battery projects. And we'll have three experts talking about these. Sergio Sainz from ATA Storage, Martin Anderson, Head of Research at Aurora Energy Research, and Anne Yu, who will be also speaking on behalf of Customized Energy Solutions. So, right, so I'm just going to wait for the panelists to join. I can see that all of them are there. So whenever you're ready, just start showing your cameras. I can see all three of you. Welcome, Anne, Sergio, and Martin. How are you today?
Hello, everyone.
Hi, Carlos. Doing well, thank you.
I'm doing well too, thank you.
Great. Well, thank you for joining us today. So, you know, as it's customary, I'm going to ask each of you to introduce yourselves very briefly, and then we'll start with Sergio's presentation, which is the first one. So, Anne, could you please tell us briefly who you are?
Sure. Thank you, Carlos. Hi, my name is Anne Yu. I'm with Customized Energy Solutions. So CES is a services and consulting company. We actually help manage over 14,000 megawatt of resources around the US, most of them solar and wind. And we also help manage over 400 megawatt of energy storage, again, in different places around the country. So my role at CES is within the emerging technology team, and we really help a lot of different developers looking into getting into the ISOs or integrated markets in the US, and really help them understand the revenue streams, the local rules. How do you come in as a storage or as a hybrid developer? So that's kind of where my expertise is. My focus is specifically on California, but today I'm going to talk more in general about other markets as well. So happy to be here.
Thank you very much, Anne, and welcome to the session. Next up, I'm going to ask Martin to introduce himself briefly.
Great, thank you, Carlos. Hello, everyone. I'm Martin Anderson. I lead up our research team for Aurora Energy Research. I'm currently based in Austin, Texas, originally from the UK. Aurora as a company as well as a global power markets research company. We focus on forecasting the wholesale and ancillary markets out to 20, 30 years, out to 2050 and beyond as well. Originally, company started over in the UK, but expanded out now and covers many of the global power markets, covers a large amount of Europe, and also PGM, kind of CAISO as well for the US markets. And looking forward to going through some of that analysis today as well.
Brilliant. Thank you very much, Martin. So, and well, Sergio, if you could introduce yourself and then get ready to present.
Okay, thank you very much, Carlos. My name is Sergio Sainz. I am the head of any storage department in ATA. I have around 10 years of experience in energy storage. I started working in storage in an EPC integrator company. I had the opportunity to work in several projects around the world with different technologies, with lithium ion, with NMC, LFP, with flow batteries, NAS, and so in the design, integration, commissioning, and operation of battery storage projects.
Brilliant. Thank you very much. So as soon as my mouse starts responding again, I'll stop sharing my screen. Yeah, there we go. And you can start sharing yours and just begin your presentation.
Okay, you control the presentation, Carlos, or?
No, my I
Okay.
thought you'd be sharing it. So if you have it at hand, you can share it. If you don't have it at hand, let me know and we'll share it on your behalf.
I'm going to share the presentation. Okay.
It's better that way. We don't have to say next slide every time. I can see it. So if you put it on full screen now.
Okay, can you see my screen?
Yeah, I can see it perfectly. So please, over to you whenever you're ready.
Okay, thank you very much, I'm going to talk about the design parameters influence of on storage business model. I will give you a technical point of view in this presentation regarding the business model. First of all, let me talk about our company. Only very brief presentation. I lead the ATA Storage, the storage division in ATA Renewables. We are a technical engineering company with more than 15 years of experience in renewable sector. We have experience in more than 50 countries. We have offices in Spain, in Italy, in Australia, and in Mexico, and we have more than 180 gigawatts of experience in projects around the world, in more than 2,000 projects in our experience. 2 years ago, we created the ATA Storage. It's our brand in charge of the energy storage and hydrogen projects. Basically, we are the technology market, the integration and hybridization expert in the company. Okay, let's go. Basically, our objective here is to talk about the influence of several design criteria or inputs on the business model from a technical point of view. Okay. We'll talk about the type of the application, the combination between power and energy for different applications, the duty cycle, that is important also in this, basically because it's important in order to size the system, and in order to also, we need to take into consideration that the ATA suffer degradation also. We will focus on the battery technology selection also. We need to take into consideration the project life of the project. We will very focus on the sizing strategies, very important in order to define the beginning of life strategy or end of life strategy, to maintain the capacity, the performance warranty, and so on. We will talk also about the heavy configuration, and we will finalize talking about the price of the batteries. Okay. In this presentation, as we have here a lot of parameters, we will focus only in one of these parameters. Okay. In order to optimize the profitability of a battery storage project, it's very important in the development stage to optimize the size of the batteries, basically the power and the energy, and the optimal dispatching of the batteries in order to maximize the revenues, taking into consideration the stacking services. Actually, here we are talking about the market, real-time market, secondary frequency regulation, and speed increasing in United States. In this case, normally we use our optimization tool. It's an in-house tool in ATA. And we use as inputs the configuration of the plant. If it's a hybrid plant with a standalone plant, the configuration, the coupling configuration, the DC or the AC configuration, the information from the renewable plant, if we have a renewable plant, CAPEX, OPEX, and market price forecasting, ancillary service price forecasting. We have a tool in order to maximize the profitability of the project. We model the market equation. Here we can see the market, regulation up, regulation down, and so on. We model the technical equation in our tool. And at the end of the day, we get the optimal size, the profitability, optimal dispatching, degradation of the batteries, and we get a sensitivity analysis regarding different parameters, as the different price forecasting, different configurations, different CAPEX forecasting, and so on. Okay. And here we are going to see some examples in the analyzing the parameters design on the business model. Okay. Actually, here we have a optimization use case working in the day-ahead market and the frequency regulation market. Here we have a battery storage plant collocated with a PV plant. This is only an example, a PV plant of 155 megawatts. And here we can see as we get the optimal size for the batteries is a battery storage system of 57.5 megawatts 2 hours. And here we can see how we get the optimal size of the system. This is an example in the ERCOT market, and basically the thing we see is that for example in ERCOT market we are getting optimal size for around 1-2 hours. And if we go to the CAISO market, for example, we are getting an optimal size for 4 hours, more or less. Another important point is the technology we use. If we focus on lithium ion, as you know, we have NMC technology or LFP. Here we have a table with a comparison between the different technologies, and this is important in order to analyze what is the impact in the business model regarding the technology you use. No. Basically, here we have an NMC technology we can use in applications from minutes to hours. It's for more flexible, and LFP normally work between 1 and 4 hours. Energy density for NMC normally is higher. We have normally 5-6 megawatt-hours in 40 feet containers, and for LFP normally we have a lower density, and we integrate normally 4-5 megawatt-hour in a 40 feet container. The degradation obviously is different. Normally when we see the degradation curve of an NMC technology, we see a smoother degradation in the first years of the project. For LFP technology, normally we see a deeper degradation in the first years, and this degradation in the rest of the years suffer a relaxation and in the degradation, and the degradation is smoother. Okay. Another important point in the lifetime is normally the state of health of the NMC is up to 70%. For LFP, is up to 60%. This permit a longer life. The safety, well, everybody talk about the safety with NMC. We have a more aggressive thermal runaway if we compare with LFP, but at the end of the day, if we install enough safety systems, basically a battery storage system, we can say that is a safety system. We don't need to have problems. Taking into consideration the price, normally for more than 2 hours, LFP is more competitive. But if we talk about the references, we have more projects, more references in the last years for NMC, but in the last 3 years, maybe we have more projects of LFP. Basically, at the end of the day, the selection of the technology depends mainly of the application. Although NMC has traditionally been the most used technology, today LFP is widely used for application for more than 2 hours. Basically, thanks its competitive price. Another important part is the application and the degradation of the batteries. Here we have a use case for a battery of 2 hours for 1 cycle per day, 1.5 cycle per day, and 2 cycles per day for LFP technology. For these 3 scenarios, we have the lifetime of the project. If we consider this duty cycle, okay, basically with 1 cycle per day for 2 hours batteries, we are going to have around 20 years of project, with considering the minimum state of health of 60%. For 1.5, we will have around 19 years. For 2 cycles per day, we will have around 14 years as maximum. Okay. This is important when we can define the maximum cycle we have in our project. Normally, the cycle is for any application. We have a cycle, but sometimes we can define a maximum cycle. You know, if we compare for FP technology this duty cycle, we can see as maybe 1.5 cycles is advantageous duty cycle for the business model, because present a good trade-off between the use energy and the lifetime of the project. Here is important also to take into consideration the performance warranties that you get from the battery supplier, for the battery integrator, because for LFP, for example, you can have a minimum state of health of 60%, but some battery suppliers, for example, provide performance warranty only up to 65% or 70%. This is important in order you want to have a project with a performance warranty for the entire life of the project. No? The sizing strategy maybe is one of the most important things in order to define your business model from a technical point of view. Here we have defined the 4 strategies. The first of them is a beginning of life strategy, working a maximum the depth of discharge. In this case, we design the system with in order to provide the energy only beginning of life, and we will have a degradation, taking into consideration the duty cycle of the system. We will assume this degradation in our business model. Okay. At the end of the day, we will have a performance warranty from the battery supplier following this curve. Okay. The second strategy is the end of life strategy. When we have a usable energy constantly required. Okay. Basically, we are going to provide a constant energy for the entire life of the project, and we will have our sizing at in the beginning of life, and normally we will have augmentation strategy. Okay, and normally we will have a DoD retention, and we will not use all the capacity of the batteries in order to maintain this capacity. Okay. The battery supplier or the battery system integrator we will provide us a firm capacity performance warranty, okay, and we will use only the constant energy required. Okay. A different strategy is if we want to use all the energy we have, because when we have a constant energy, the degradation curve it's going to be less aggressive because we are not using the maximum DoD. But if we compare the energy we are using and the extra energy we have, sometimes maybe it's not very good for the business model. For a reason, we can maybe go a strategy with using the maximum DoD and having a minimum energy for the entire life of the project. We can define this at the beginning of the project if we sign, for example, a flexible performance warranty with the battery supplier, and we can change in the project the DoD or the cycling, or we can change other parameters because we sign this kind of contract with the battery supplier in order to use the batteries deeply, maybe in some years, in order to get more revenues. Another strategy is very typical also is when we have a minimum energy required in some year of the project. Okay, for example, here we are showing a minimum state of health in the year 12. Here we can see the different degradation curve for the different strategies. Okay, at the end of the day, as conclusion, beginning of life sizing presents less investment cost. It's obvious. And end of life sizing requires to be compensated by higher revenues. Normally, end of life makes sense when we have a requirement of an annual throughput of energy. For example, if we need to provide a capacity service, and we need to provide, for example, for a fixed number of hours. No? The last technical point we are talking about in this presentation is the hybrid configuration, this AC or DC coupling. For AC coupling, as you know, we have it's a system more flexible regarding the business model. We can provide services separately. Okay. The problem is we cannot avoid the clipping effect, or we are going to have more losses in the charge of the batteries. In the DC coupling, we are going to have less a better efficiency because we have less equipment, and we are going to avoid the clipping effect and so on. Okay. At the end of the day, for us, if we compare the CapEx, obviously for DC coupling, it's going to be lower. If we compare the RTE, the efficiency of the batteries, it's going to be higher. But we are going to have a system less flexible in order to provide ancillary services, for example. For us, maybe the most important consideration here is to consider your business model. Okay. Another point that is not technical, but I think it's important to highlight here in your business model is the price of the batteries. As you know, in the breakdown of a battery storage project, the batteries are around 60, depends on the energy of the project, between 60, 80% of the project. Obviously, the price of the batteries is significant in the business model. In the last year, the price of the batteries rise a lot. We can give, for example, some numbers. In 2020, before the raw material crisis, the capex of the batteries depend on the project, the peak rate, and so on. Was around between $300 to $250 per kilowatt hour, more or less. It was expected that in the next years we will have a reduction of the price even up to 50% for the batteries, not for the battery racks. Today we are in conversation with the battery suppliers. We have agreement for them. We are every day talking to them. The price of the batteries is rising every month in the last year. We have even price even 30% more in the last year. Obviously, it's the current situation. Maybe when this crisis recover, the price recover also, and we recover the trend of the reduction of the battery trend. But the point right now is we have a very high price for the batteries, and depends obviously the market. If we go to markets as the United States, mature markets, maybe the market will continue to grow, but in emerging markets, obviously this is going to be very bad for the business model. And basically, this is my presentation. Thank you very much. I will happy to respond any question at the end of the session.
Thank you, Sergio, for your presentation. Very insightful. I knew that prices had gone up, but I had no idea that they had gone up by 30%. So that's that's quite an increase. And as Sergio said, please, to everyone in the audience, do send your questions through the Q&A box. We already have a few questions there that you can start answering in writing if you want to. And without any further delay, I'd like to give the floor to Martin Anderson. So Sergio, whenever you can, if you can stop sharing your screen, and then that will let Martin start his presentation.
Great, thank you, Carlos.
So for those of you who maybe joined later, so we're definitely recording this session, and you will get an email with a link to the recording and the slides. Sergio, can you please stop sharing your screen? If you're looking for where to stop, is normally at the top is a red thing that you press and you stop sharing. Are you okay there? You can't find it? There we go. No problem. Thank you, Sergio. Martin, over to you.
Great, thank you, Carlos. Thank you. Really interesting to see how the the different dynamics and different aspects impact the battery business cases. And looking forward to diving a bit more on the business case side and looking into the revenue futures for batteries. So that brought together a few slides, a selection of content here to really try and answer three questions. We're going to be focusing on the ERCOT market. So great to see Sergio was also looking at the ERCOT market, and we'll maybe touch on why that's of such interest at the moment. But I'll try to answer three questions in my session. The first one is, what have batteries been doing in ERCOT to date? How have they been operating, and which markets have they been operating in? The second question is going to be what they're going to be doing in the future. So how is that going to change as you get more batteries coming through to the market? And the third question is going to be on what that means for investors. How much can they expect from their returns, and what's the optimal configuration, both in terms of location and in terms of duration for the batteries? So I'll try to answer those three main questions as we're going through the analysis. But just to touch briefly at the beginning, just on about Aurora. So I mentioned earlier on, Aurora, we're an energy research company focused on power markets. And we cover the majority of European markets now. We have offices in the UK, in Madrid and Germany and Paris. And we also cover Australia and increasingly the US markets as well. So currently have offices in Oakland, in California, and in Austin, Texas, where I'm currently based. And we're covering at the moment PJM, ERCOT, and CAISO. We're about 250 people. I think we're one of the largest companies focused purely on power markets and the modeling of those markets. And we offer services both in two ways, both in terms of research and subscription services, and in terms of consultancy as well. So we have about 550 companies subscribe to our analysis. They get our regular reports and deep dives into analysis. And through consultancy, the majority of that work is through transaction support. So last year, I believe we supported around just over 100 transactions. And a lot of those actually for batteries as well. I think we've supported now about 1 gigawatt of operational batteries across different markets. So covering those markets we've operated in the UK, Germany, Australia, a lot of those markets have already seen batteries come through, majority being supported through capacity market payments, and therefore seeing a lot of battery capacity deployed across those markets. And obviously modeling of batteries isn't straightforward. There's a lot of complexity that comes with modeling those. It's a relatively new technology, and how it operates in the market is also relatively new as well. Essentially, with regards to the approach that we see, essentially the hard part that we see is the future of those markets. As you see a number of trends coming through, we're going to see renewables coming through, electric vehicles, a wider change, as we mentioned earlier on in the previous session, the coal retirements as well, so retiring thermal capacity. A number of changes coming through for these markets, and ultimately modeling the consistency between wholesale markets and ancillary prices. At the same time, we see batteries coming through is where we see a lot of the complexity that comes with it. But we model those prices, and then we use those prices to then estimate values for the battery can be making within that market. So given those price series that we've estimated for future years, how much can batteries make against those prices in the future as well? So that's often how we approach these problems for tackling battery valuations. And so we're talking about ERCOT here as well. There's obviously lots of interest. I'm sure it's been tackled in a number of other sessions as well, but obviously lots of interest in batteries and ERCOT. I think when I was first looking at ERCOT and batteries about 18 months ago, there was about 20 gigawatts of batteries in the pipeline. We're currently at about 50 gigawatts of batteries. So a huge amount of batteries trying to come through, both the mixture in terms of standalone projects and also co-located. Majority of those co-located projects are looking at solar and storage co-located. And we're also seeing obviously a variety of locations as well. Majority of projects trying to get through in the north and the south areas for batteries coming through at the moment. There's about 1.2 gigawatts of batteries operational at the moment. So that is a small amount compared to the huge pipeline of projects trying to come through. And so a wide change coming through as more of those batteries do come through into the ERCOT market. And obviously this is going to be a change we're seeing across other markets as well. Very much expect that ERCOT is at the front of this transition and more batteries coming through. And we'll see this change across other markets globally as well going forward. But back to those three questions I was trying to answer then. So the first one I want to tackle was what batteries have been doing in ERCOT to date. We've seen there's about 1.2 gigawatts of batteries currently dispersed across ERCOT at the moment. And before even thinking about what batteries can be making in the future, you can start and see what they've been doing in the past. So I'm highlighting on this slide how batteries have been operating, using 2020 as an example, how batteries have been operating in ERCOT. And I've used three different example batteries, which are all showing different strategies for how they've been operating within the market. The first example that I pulled out here is a battery that's been focused purely on regulation services. This is a 30 megawatt battery, which is a half hour in duration, and that came online in 2017. This battery has predominantly been working in regulation up and regulation down. I'm highlighting here the 2020 market participation. So essentially this shows in a given hour, is it operating in regulation up or regulation down? And essentially this shows that almost 200% of the time, that essentially means that in every single hour in 2020, it was pretty much operating both regulation up and regulation down in those hours. It wasn't necessarily providing up to its full capacity, but it was at least providing some regulation services. Regulation services, for anyone not familiar with ERCOT as well, essentially the frequency balancing services. Batteries can respond very quickly. This battery in particular was participating in the fast reserve services, so automated essentially in how it's providing those markets. Regulation services, relatively small markets as well at the moment, about a few hundred megawatts in size. And the fast reserve service is around 60, 70 megawatts. So this battery providing quite a bit of that regulation services. But in terms of the money it's making, about $100 per kilowatt for 2020. We've seen previously the CapEx estimate for batteries on Sergio's graphs around $300 in 2020, I believe, maybe around $300 to $400. So $100 per kilowatt for a given year is pretty good in terms of your gross margins and how much money you're making. The other battery example we're showing here, so the second one is responsive reserve service. So this is more the reserve service which you're providing, essentially capacity payment just to be available if you need to turn up normally or not called upon too often. It's more a few times a month that you would be providing that service, but essentially getting capacity payments to provide that service and be on backup to provide that service very quickly. For this battery, we're seeing that it's a 1 hour battery, so it's able to provide that service. 10 megawatt battery, so smaller than the other one. And it's essentially operating all of its time in that response reserve service, 90% of the time, and a small amount in energy arbitrage when required to, or when particularly lucrative to operate in energy arbitrage during those times as well. But we see as well for this battery getting similar returns to the first battery. In terms of returns it's getting. The final one that we're showing is cross-market optimization. So rather than picking one specific ancillary service to operate in, try to optimize across all of those markets in a given hour to maximize your returns. There's many companies that go out there looking at optimizing the returns of the batteries and how those are operating. And we're seeing that this one here is operating a combination of the regulation services, the RRS, and also energy arbitrage as well. So a combination of those different services. Essentially see that it's coming up close to 200%, around 150%, so combining both RRS and regulation services at the same time. And in terms of the returns it's getting, it's again coming close to $100 per kilowatt. For these last two batteries as well, I should say that they came online during 2020. The last one in particular, the cross-market optimization, came online in October. These numbers are prorated to take into account for that, but essentially highlighting that this battery missed out on the most lucrative time of the year, which is going to be the summer months, when you're seeing the highest prices in the wholesale markets and the ancillary markets. And we're seeing that this battery was still performing very well. If you actually look at those specific months, we see that this one was outperforming the other two batteries as well. So essentially highlighting that there have been different business models to date. We've seen that the most lucrative one for 2020 at least has been this cross-market optimization, and increasingly seeing that that's going to be more important as we're going through and you're getting more batteries entering the market, wanting to optimize across those markets. The next question I wanted to ask was then what batteries are going to be doing in the future. Without giving too much away, we see it more aligned with cross-market optimization. But I want to touch briefly just on the methodology that goes behind this as well. We are a modeling company, so apologies for going into the nitty-gritty of the details, but indulge me for a moment whilst we spend just touching on this, because it is complicated when thinking about modeling these markets. When approaching to model the forecast for these batteries and how they can be operating, we split it into two main steps, which I alluded to before as well. The first step is to model the wholesale and ancillary markets. So that's sort of bottoms-up approach when taking into account. This is across 20, 30 years in the future as well. Essentially, if we're modeling the future of electricity markets, you have to model the economic decisions that are going to be made to estimate how investors are going to be thinking in the future as well. So that's essentially the approach we take to make sure that investors get the returns that they need across power markets. So we make assumptions around new capacity that's going to be entering, whether that's cost for new wind and solar projects, and also for the cost for existing thermal plants. When are they going to be wanting to retire based on the revenues they're making? That essentially means that we end up with a consistent approach, and we end up with consistent hourly prices coming out of this as well. We see wind capacity building when it's profitable, but you wouldn't necessarily get wind overbuild if the cannibalization becomes too extreme as well. At the same time, we see batteries entering when they can get returns and get the returns they need from ancillary services. If you have too many batteries building, then that will put a balance on things so that you're ensuring equilibrium and stability across the returns that you're seeing. So overall, a consistent outcome. From this first step, we generate wholesale prices and ancillary prices, which are consistent with one another. What you don't want to be doing is to just making up the ancillary services or assuming they're going to be constant throughout the year. There is always consistency between the two, and you do have to model those on an hourly basis, so you do have that consistency. But once we have those hourly prices, then move to the next step, and that's essentially then looking at how much your battery can make given those prices. Given your battery is going to be dispatching against those prices, how much money can it be making? And so that takes into account different business models, whether it's operating in ancillary services or wholesale only, takes into account different duration, different size of the project, degradation, different technologies, all of those different parameters which may impact how your battery can operate. And that gives us a forecast for how much batteries can operate in the future and how much money they can be making. So thank you for indulging on the methodology. Given that and given how much batteries can be operating, we do see a fundamental shift essentially in how batteries will be generating their profit in the future. We saw historically, we're showing here an example battery that we're looking at. It's a 1 hour battery in the West Hub, which historically has been operating predominantly in RS. We see the battery lining up closely with the battery example, which is operating across different markets, historically around 50 to 60% of its revenue coming from RS, with remaining coming from regulation up and also some from wholesale arbitrage and regulation down as well. Going forward, we see that change. So by the time you go to 2030, you're actually seeing a fundamental shift away from 20% of your revenue coming from wholesale arbitrage. Instead, it's going to be 80% that's coming through from wholesale arbitrage. And instead, the ancillary services are going to be making up a less proportion. Ultimately, during this time, we're seeing a wider change in the ecosystem. There's more renewables coming through. You're going to see more volatility driven from that as well, increasingly renewables setting the price at lower amounts, which is going to be great for batteries. At the same time, you're still going to see moments of scarcity, and batteries are going to be dispatched at those times. So increasing batteries operating in wholesale markets, more in the realms of energy arbitrage, but still operating in ancillary services when available as well. Obviously, the big change also coming here is increasing amounts of battery capacity. Within our forecast, we see around 10 gigawatts of battery being deployed in 2030. So that takes into account essentially the pro-rating of ancillary services come through. There's more batteries coming through. You have to share those ancillary services around, and you can't guarantee just always being able to continue that business model. If we saw those batteries earlier on, 2 of those operating solely in individual ancillary services. By the time you get 10 gigawatts of batteries coming through, those ancillary services have all been fully fulfilled essentially from batteries. So you're having to share around those ancillary services across multiple batteries, therefore looking to seek into the wholesale markets to get the returns that we need as well. So ultimately seeing that big shift, and we see that then going on from 2030 out to 2040 as well. In terms of returns, I still see that can get the returns that you need for investors. Declining, we see the forecast declining from around $110 per kilowatt for batteries in 2022 down to around $50 per kilowatt per year in 2030. So whilst that does reflect a reduction, at the same time, we do expect the technology cost to continue reducing as well. So as your capex cost to continue to come down, you can still get the returns that you need to as a new investor. And we still see capacity increasing out to 2040 as well. So essentially seeing this being as an equilibrium outcome in terms of batteries getting the returns that they need to and still building when they can as well. So that answered my second question. In terms of what this means for investors then and the returns that they can expect, these numbers highlighting here the IRRs we can expect for batteries across 3 different dimensions, across different years of entry, so looking in 2022, 25, 2030, across different durations, 1, 2, and 4 hour, and also across the different hubs as well. So if you are, essentially what this shows is if you are looking to deploy a battery in 2022, deploying a 1 hour battery in the West, maybe that gives you the highest returns. We see that as seeing higher amounts of price variability, capturing higher spreads, whilst also being able to get the operating ancillary services weren't available as well. We see that 22% being highest in the West, but still good returns across other hubs as well. And this will vary across many different nodes as well. So this analysis being done at hub level, when looking across many of the US markets, it's actually going to matter exactly where you are, how congested your local location is, and that's going to have a big impact on the wholesale revenue you can expect and the price formation at those different locations as well. So that can also potentially lead to higher upside than this as well. In terms of the duration, so we see 1 hour duration coming out on top. We see that largely driven to the ancillaries that is helping to derive that additional revenue. For batteries, moving towards 2-hour and 4-hour battery, you don't necessarily get an additional revenue from providing ancillary services. So see that 1-hour batteries are best placed to provide those. And moving towards higher duration batteries as well, we don't necessarily see the price spreads coming through to get higher returns for those batteries as well. So overall, see that whilst the gap will narrow over time, still see that 1-hour batteries can get the highest returns across those different batteries. Great, that was answering the 3 main questions. There was one last slide I wanted to touch on, was maybe just different strategies for managing that risk. Ultimately, batteries are still a new technology. Investors are getting comfortable with the technology as well, and there's a few strategies that you can use to try to manage that risk that comes with those. There's portfolio diversification, both across regional and technological diversification, if you're looking at power assets, so buying batteries in different regions, different markets, to try and diversify some of that market risk, but also different technology types as well. So combining a portfolio with wind and solar and other asset types as well. One way to try and manage that risk. Co-location with renewables, Sergio touched on as well, essentially a function of portfolio diversification, but very site specific as well. Potentially cost savings that come with that, providing benefits for your assets. Offtake arrangements to try and de-risk for batteries as well, though likely coming at a cost in terms of your revenue, like you have to take a haircut in terms of that. And finally as well, potentially any additional government support as well, and policy, seeing some states adopt those mandates, and if that comes with additional support, then that can help to de-risk these projects as well. So great. Well, we're touching on batteries, going through some of our analysis. This is from a previous forecast. Subscribers of ours will be able to access more up-to-date analysis and more recent numbers. But if I give you 3 main takeaways from these insights, essentially the pipeline for batteries is huge, around 50 gigawatts of batteries trying to get through at the moment. We see that batteries will increasingly be operating wholesale arbitrage as the ancillary services become saturated. But there are other ways to manage battery risk as well that may come from these investments that I just touched on. So thank you for listening. Looking forward to any questions that may come up at the end of the session as well. But that's all the slides I want to present.
Thank you very much, Martin, for your presentation. I think we have a few questions. You can start answering them in writing right now. But right now, without any further ado, I'd like to give the floor to Anne Yu. Anne, whenever you're ready, I can see you have started sharing your screen. You put it on full screen mode.
Yep.
Yeah, perfect. Hi. I can see. So yeah, over to you.
Thank you, Carlos. Hi, this is Anne Yu from Customized Energy Solutions. So thank you, Martin and Sergio, for really kind of laying the landscape here, and then kind of introducing to the audience in terms of where storage is in different markets. So today I really want to focus and hone in specifically on the hybrids, and this is related to the new revenue streams. And I'm going to talk about why this is kind of new, but not really new. So again, a little bit on CES. So we are a consulting and services company, but I think our advantage really lies in that we're actively managing clients' generating facility. It's over 14,000 megawatt in different ISOs around the US, and then most of them are wind and solar. And we also manage over 400 megawatt of energy storage. So and then we have a lot of different people monitoring the ISOs and RTO markets around the country. So it's really, for us, it's really being able to bridge that gap between what's being the policy that's being crafted in the ISO and RTO region, and bring that into the operational side, and how do you translate between that, and what does that look like going 20, 30 years into the future. So today I really want to focus and talk about hybrids. So hybrids is not really a new business model, I would say, when you think about storage, because common sense would be, storage is it's a natural marriage between storage and renewable. You try to shift the energy from when you need it the most, and then you are trying to firm again against the renewable intermittency. So really, what is new about putting storage and renewable together? They are such a natural pair. But when you come from the grid operator's point of view, there are different questions that they would think about, right? So why would you dedicate one storage resource or handcuff it to just one intermittent resources? Why can't you utilize, the battery for more different resources? And then when you're looking at a combination like that, it is not really a one-on-one replacement with a traditional fossil unit, because you still have intermittent renewable, but at the same time, the storage is kind of limited in its duration. So can you really do that replacement? So I think the point here is that I would say it's still kind of early days for hybrid in general in different markets. So this reminds me about 10 years ago when I was in one of ERCOT stakeholder sessions. And then this is, 10 years ago, so people are still quite unfamiliar with what storage does. So I was explaining to the stakeholders that storage can actually do generating, can actually be a generator and a load at the same time. And then I hear the gasp in the room, like, oh, we didn't know that this is how you would use the resource. So it's a lot of educating and making sure that people understand the versatility of the resource, and really being able to like wrap their heads around, how do you operate it? So one example that I can think of here is that we actually helped a client in a particular ISO before, in terms of they're trying to look into a coal plus a storage plant. So the idea is that they want to use the coal for the energy portion, load following piece, and then the storage plant for ancillary services, basically doing frequency regulation or any type of fast responding resources. So they want to be able to like switch between these two type of resources. But when they try to register the resource with the ISO, there's only one parameter for ramp rate, and it's not a dynamic one. So you cannot switch on and off in terms of what you wanted to do. So for example, if you register, the ramp rate of the storage, you'll get a different type of schedule in terms of load following. But if you register the ramp rate of the coal unit, you won't get any ancillary services at all, because it's going to be disqualified for how slow it's reacting. So these are the sort of the nitty gritty pieces when you look into in terms of how do you put a hybrid plan, in the ISO, because there are so many details to look into. When we're talking about a hybrid configuration like this. So here, it's really sort of a list of reasons why you would think about adding storage to renewables. And, Martin and Sergio both touched upon this in terms of the fixed development costs, and, why not, if you have extra land, if you already have an interconnection, why would you not put a storage together with the renewable so that you can actually even out some of the development cost? But I think the largest economic driver right now is really, especially for solar plus storage, is the investment tax credit from the federal level. Is that if you can charge, the storage can charge directly from the solar on site, then you get this tax benefit. And this is really, in a lot of the economic incentive that we're seeing for the newly developed projects. Also, you can increase your PV production by just mitigating the clipping and any curtailment. The extra PV production can also count towards your REC. That means you're really generating more certificates in more hours. Other consideration include, utilization of the interconnection. You can have a array size larger than your point of interconnection limits, and really try to balance out, between what solar produces and what storage can do. Shifting your solar injections to improve LMP. This is kind of what people think about when they're trying to think about pairing storage with solar, is really trying to capture or shifting the energy to when it's needed the most. So these are really, different reasons that you would consider adding storage to a renewable project. But then how do you go about doing it? I think that's kind of the key piece that people really wanted to understand. So first of all, I would say would be understand what the local rules are. So where is your project site? Is it in ERCOT? Is it in CAISO? How are the rules different? So we kind of we've been using the term co-located and hybrid kind of interchangeably, throughout, but really they mean different things in different ISOs. Like, what do you mean by co-located? You're just putting two resources on the same piece of land. Are they sharing the same POI? Is the ISO able to meter and monitor the output of each of the resources? And where do you put the meter? Where is the telemetry? So So how are the ISOs, looking at these particular resources? And each of their configuration might be a little bit different depending on, where you are. So that's kind of the sort of the first step to understand, what are the resource model that you're trying to participate in with this project. And then once you kind of figure that out or know your different options, then you would plan the stack value. So it's what Martin was showing earlier in terms of the different values that you can provide in the ERCOT market, whether it's regulation, it's RRS, or you're doing energy, what are the different stack value that you can look at? And they're going to be different depending on where your location is. And then it is the battery sizing exercise, right? So everybody is trying to figure out this magic number in terms of, what is the battery to solar, what is the right battery to solar ratio? Is it a third? Is it half? Again, it depends on where you are in the market, and then the different services that you really want to provide, considering your ISO participation. So I would say you really need to understand the rules and then know what services you want to participate. And then that is the battery. Then you come to the battery sizing exercise in terms of, how do I manage between my cost and the revenue? So that's the next step. You estimate you model the incremental revenue if you add a storage in. And then, how does that improve it's not just the wholesale piece of the revenue, but your other, rack and other type of contract that might be beneficial from adding a storage to it. And then you go to the financial analysis or the revenue and cost scenarios to figure out, what is the final return on investment if you actually add storage. So again, Sergio showed this earlier in terms of, whether you are coupling with DC or AC with your storage. So I would say there's a lot of different considerations, when you're looking at this, and from our perspective, it is really, when you're doing DC couple, I would call it a true hybrid, because you are a black box from the grid operator's perspective. They give you an instruction they wanted you to follow, but in terms of how do you manage that responsibility between the solar and then the storage is really up to your optimization or your operating platform in terms of how do you follow the signal, but at the same time kind of maintaining the battery state of health and also making sure that you utilize the solar output completely. So there's just a lot of different technical and also market consideration when you're looking at the hybrid configuration. So an example here is that it's one of the projects that we did in ERCOT, but it's really a comparison between whether you are trying to get ITC or not. So I know there's a lot of colors here, but really what you wanted to look at is really the dispatch schedule here. So you can see that the graph on the left is one coupled with grid, meaning that you're charging from the grid. So essentially you're not getting the investment tax credit because you're not charging solely from the on-site solar. And here is what you're doing when you're charging from the on-site solar. So the difference between these two, you could see that there's a lot more regulations scheduled here versus here. So this is essentially when you are you are restricted to not charging from the grid. You can only regulate around your solar output when there's a lot of solar. So essentially, you have say 50 megawatt of solar output and you're regulating, let's say 20 megawatt around that 50 megawatt. So you're not charging from the grid. That's when you can provide the regulation without violating the ITC rules. But around here, since you're not looking at the ITC anymore, it's really, you're trying to optimize around, what services you can provide. So this is kind of the detailed comparison that you will look into when you think about, all these hybrid configuration, where they are located. How do you try to optimize your revenue, considering all these different aspects of what you can do. And then, again, coupling back to what Martin was saying earlier, is that what is the duration? What does the duration look like, and how does that affect your different operation in the market? And that, coupled with your operating strategy, will kind of give you a better understanding of how do you make the most of your hybrid project here. Okay, so this is really mainly what I wanted to share. It's fairly short, but I really wanted to leave some time for the questions. Back to you, Carlos.
Thank you very much. And we have, well, about 5 minutes actually to answer one question, I suppose. So, I think, I don't know if there is one that you have all seen on the screen that you think, yeah, we should definitely answer that one. Otherwise,
sorry.
I could ask, do you, and, that there are, well, relatively few hybrid or co-located projects. Why is that?
Yeah, so sorry, I can address the question in the text later, but essentially, yeah, the reason why I think the reason why we're seeing relatively few existing hybrid project is because people are really still trying to figure out. So you can see a lot of them in the pipeline in ERCOT and also in CAISO. People are really trying to get into the queue, having these projects. But I think right now the reason why there aren't that many is just because the rules aren't that clear. People are still trying to figure out, how do you really truly operate a couple together hybrid? Yeah, that would be my answer. Carlos, do you want to jump to the questions, or how do you?
Yeah, I'll jump. I'll choose some of these questions that we have here. So, right. So we have one that I think is quite general, but it's very interesting. What are the key factors that affect the capex of battery energy storage systems? So, Sergio, you started answering that one, but then you're on mute, by the way, just in case. You're still on mute. Still on mute, Sergio. We can't hear you. Yeah. Okay,
Sorry.
there we go.
It's very late in Spain. And the main factor for the battery storage cost, basically, as I mentioned before, the battery racks cost is the main part, represent about the 70, maybe more, depends on the hours of the project. And this is basically the main factor. Taking into consideration the battery racks, the raw material the lithium is basically the critical part actually now today with basically is one of the problem we have right now is the price of the lithium, but in the battery because at the end of the day the breakdown of the prices, if we consider the price of battery storage, the power converters can be around 5%, the EPC around 8%, something like that. Okay, the most important part is the battery racks, and in the battery racks, as I mentioned, it's important to size correctly the system. Because at the end of the day, the deposit charge of the batteries, the efficiency, if you don't design, for example, correctly your system, you will have a good efficiency in your system. At the end of the day, you will need to oversize the system. There are different factors in taking into consideration the sizing of the battery racks, but mainly the batteries are the most important part in the cost.
Thank you very much, Sergio. And there is a question here which I think you could probably answer, Martin, which is by Manda, and if asked, if direct pay is introduced, what would that make a specific application case more beneficial than others?
Very good question. I think for direct pay, it obviously takes a bit of the complexity out in terms of using tax credits for projects. I would say at the moment, I think my current understanding is the investment tax credit, as Anne kind of mentioned, is available to batteries co-located with solar. So that's kind of the only aspect, you can currently get support for batteries. What would really be a bigger change is if you have the standalone battery ITC, and if that is made available. That was currently floated in the Build Back Better legislation that Biden is trying to push through at the moment, so it would be a federal wide. If that was then made available, then that would give additional support for batteries as well going forward. Direct pay, it wouldn't necessarily change the money that's available, but maybe takes off some of the transaction costs and makes these deals more simple as well. So could incentivize something, de-risking some of these projects potentially, and making them more likely to go through as well. So making the transaction costs lower for those projects as well. So I think the direct pay is one aspect, but also wider battery support under the investment tax credits, another aspect which could be interesting and is ongoing at the moment with regards to how that's going to develop.
Thank you very much, Martin. And then, one last question before we go to the next session, which is, well, it's more than a question, is a statement really by Jamie Marcus, who has been saying, well, yeah, everyone talks about gigawatts of batteries, but what about CapEx? What about investment into these sectors? So do any of you have, figures on how much is being invested year on year in the US, or how much is forecasted to be invested in batteries? And if you don't have the figures at hand, then, well, that's a short answer, then means that no,
I just
we
did
don't
a
know.
quick calculation. I think if your capex is going to be $400 per kilowatt, let's say it stays at that level of combination of 1 and 2 hour batteries, we think there's going to be about 10 gigawatts of batteries by 2030. So that takes you to about 4 billion in terms of the capital cost, assuming that there's going to be some cost declines as well, but in terms of, and there could be more or less batteries as well, but it's in the billions in terms that's going to be spent on batteries going forward. So there's and this is just for one market for ERCOT as well. Ultimately, lots of other regions in the US looking to invest in batteries, so that number could be significantly higher as well.
Brilliant. Thank you very much, Martin, Sergio, and I could see that you were like furiously typing away your answer there, and I just thought, well, we can't really go to the next session before she finishes, that'd be unfair. So thank you to all three of you for being here today with us, and now we're going to go to the next session. So well, have a good day or good evening, depending on where you are. Thank you very much. And to everybody in the audience, please stay with us. We're going now on to the next session. I'm going to share my screen now so you can see who is speaking in this session. So, right, the next session is Session 4, the role of long-duration energy storage and spinning reserves, keeping the grid stable. And here we have 4 speakers, and I believe Julia Suda will be moderating this session. So, as soon as she comes in, I'll leave you in her very capable hands. In the meantime, I'd just like to remind everybody that, yes, we are recording this session. So you will receive the video recording and the slides later on. Julia, I see that you are on screen now. How are you today?
I'm good. Thank you, Carlos, so much for the invitation to be here. It's a privilege. Thank you. Thank
you for being here. So I can see that all the other speakers have joined as well. So if you could all turn on your cameras, and then, I'll let I will be giving everyone here a break from my voice, and I'll leave you in Julia's very capable hands.
Thank you, Carlos. And just to answer your question from the long duration energy storage perspective, the market that we're looking at is anywhere from $1.5 trillion to $3 trillion for long duration energy storage by 2040. So we're pretty excited about that potential too. The pie is huge for all of us because we have so much to work on. So it's really exciting, but thanks for that great question. And it was a great panel earlier to listen to. So thank you all.
Brilliant. Thank you very much. So, well, Julia, over to you.
Great. I will pull up my screen right now. Thank you. And I'm really delighted to share insights today about our organization. And let me just get it into slideshow. There we go. Can everyone see it? Thanks. Okay, yes. Wonderful. So Again, just really appreciate the opportunity to be here. Thank you so much. I'm the new executive director of the Long Duration Energy Storage Council, and really excited to share with you some insights of our organization, and also to be on this panel moderating with Raj, Hans, and Marie-Pierre. So I'll start and then hand it over to Raj. So I don't know how many of you are familiar with our organizations. We're pretty new. We started at COP26 in November last year. We are a fact-based organization, pulling together members from all over the world for societal's benefit. We're executive-led, and we're looking at all types of energy storage, so chemical, electrochemical, mechanical, gravity, to really kind of look at all the different attributes and diversity that long-duration energy storage can provide. And we are an independent organization, bringing together all these different components to really improve and demonstrate the value out of long duration and make sure that we're scaling up all the applications. And so this is our growing membership. We're really unique because we get to bring together the technology providers with the customers. So we're already having conversations about how to have partnerships and, successful leveling playing fields, and looking at a global perspective and local benefits, and kind of really weaving together all these different insights and expertise. So we're thrilled to bring all these groups together, all these unique companies and perspectives, to really start collaborating on how we can accelerate our decarbonization goals with the critical component of long duration energy storage. And as we're all working together, we've been pulling together working groups to really hone in on some really key components of where can long duration energy storage really provide its insights and value add. So I'll be speaking a little bit more about our new published report, the 24/7 Clean Power Purchase Agreement. We're pulling together a working group. And if you're interested in joining any of these, please contact us on net zero mining, transmission and distribution optimization. We have published already the report I mentioned earlier, pulling from the figures of net zero power that we launched in COP26. And I can provide that link too. There's a lot of great information there, provided from a lot of the data from our members. And we're working on our net zero heat report, really demonstrating the value out of long duration energy storage with power and heat, providing that flexibility that is so critical to the reliability, resiliency of the grid, both behind the meter and front of the meter. And then we're also putting together benchmarking materials so you can really get a good insight into the diversity of all these different types of technologies and what they can do. And realizing that, with all these different pieces, you need regulatory components and policies. And we're not advocating, but we're really trying to bring together the facts with education components of how to address various policies to help modernize and really start push forward to decarbonize. And what does this look like with a platform, funding mechanisms, matchmaking of really kind of pulling together all these different groups, and then also starting to look at regional roadmaps of various countries that have started to kind of take different components of these working factors and really kind of optimize the entire energy system. So again, this is just a highlight overview, but it's a lot of core components to why long duration energy storage is so key to the entire economy. And so when you kind of drill down into how does long duration energy storage bridge the gap between short and long duration, and it's just kind of a great sweet spot to be in the middle of this X and Y axis to really look at how we can address 8-hour plus, multi-day, seasonal, multi-month, all the different components of where long duration storage can provide value added with all the different types of mechanical, thermal, chemical, and electrochemical. And looking at low cost to high cost, about the power capex, the energy capex, really finding again that in the middle ground. Really looking at the various cost curves and then how we can provide the value of increasing the system power with lower costs. And one thing what we're really demonstrating this is showing how in the 24/7 Clean PPA report, we're noticing that there's been a lot of great work with traditional PPAs, but there are still gaps in the system. When you're trying to match energy and supply, you still have these gaps of when the sun's not shining, or the wind's not blowing, or there might be some other weather events that are causing this, that we have to rely on fossil fuels. And what we're demonstrating is that this can really impact the system and increase carbon. And what we're showing is that to fully decarbonize, we really need to make sure that these gaps are filled in with energy storage and discharging, and really utilizing the renewable energy penetration that can be there in existence over every hour slice of the day. And so what we're demonstrating too is that, this is again, filling in the gaps, but when you bring in long duration energy storage, you really are able to maximize the peaks and the valleys and really make sure that you have that clean energy that is giving the power in the supply system that equality. And so filling in the gaps, long duration energy storage provides immense value to meet the hourly supply. And again, just wanted to kind of show another way that of how long duration energy storage really can provide the longer flexibility over various durations. And when you get that sweet spot from like 60 to 80, 100% of when you have renewable energy penetration, the enormous value add of long duration energy storage kind of elongating the wind and solar potential. And so when you're looking at the 24/7 clean PPAs and really watching the time matching of the energy supply and demand, you really need, it just demonstrates how important long duration energy storage is. If you're looking at the renewable energy generation, the off takers, and just a critical component, again, how storage is needed to be dispatchable. And again, you're kind of also seeing on the graphic on the right, just to, noting where to fill in the gaps so that you really do have a solid system of solar wind generation that is for that complete 24 hours. So in addition to grid reliability and that kind of certainty that long duration energy storage can provide by filling in the gaps, we also demonstrate the tremendous value of reducing emissions. And so looking at a variety of case studies in California and Germany, seeing that, what's your grid average, and then also looks at what happens with your traditional PPAs for solar. You can get 40 to 50% emissions reduction. And then looking at maybe wind, at the PPA, you get maybe 60 to 70% emissions reduction. And then you kind of move down the trough into, really to how do you reach the 100% real emissions reductions by filling in those gaps, meaning every hour of the day with renewable energy and using long duration energy storage to help you mitigate. We're noticing that this is a huge potential and huge opportunity so that you really truly can decarbonize. And what you see at the bottom is that we've kind of introduced in the report different stages to kind of incentivize of how to get here, standardization to really promote the 80% emissions reduction is kind of getting this silver badge, and then going to 90% is a gold badge, and 100% is platinum, and just kind of having a global standardized system where there are these metrics to monitor so you really can demonstrate and be transparent about real emissions reduction. So the PPA can be both a tool to help mitigate the energy and supply demand, but it also demonstrates the emissions reduction and really filling in the gaps. So there's so many attributes that these new tools can help provide to grid reliability and security. And a little bit more on the actual standardization and the quality assessment. This was kind of brought together from membership discussions for a few months of incentivizing how to make this happen and come to reality, showing that it really can promote both renewables and promoting decreasing curtailment, in addition to the flexibility that is needed and just how you can dispatch with long duration energy storage, just additional capacity and energy. So again, just highlighting, taking a traditional tool and evolving it to do what we need it to do as we evolve and promote different mechanisms to decarbonize. And so you'll see more of this in the report, but there's just a lot of great kind of metrics and standardization components of why this is so critical to help really decrease emissions. And so this is just really kind of high level, but again, it's really exciting to see all the insights and growth of why 24/7 PPAs are a really powerful tool to use as we decarbonize, and how it is an amplifier for long duration energy storage, and really looking at hourly carbon impact, how we match in current procurement efforts and changing criteria, how we expand the targets, not to just look at 80%, but how we really can fill in that gap and meet that last 20% of emissions reductions. And additional strategies of how to deploy, as we even heard on earlier panels, the hybrid nature, kind of creative mechanisms with tax incentives or local elements of how to enhance both integration with the storage components. Because as many of you know, long duration energy storage can be both behind the meter and front of the meter and provide a diverse set of ancillary services to the grid. And it's really important that we kind of take all the tools we can at hand to really push forward and where we need to go. And so this is one of many different opportunities and projects that we're working on, but we're starting to partner with a variety of organizations of how to implement that standardized process and how to look at the different metrics to reach several gold and platinum, to really make sure that we start implementing these tools to make sure we're utilizing renewable energy as much as possible, and then really getting the biggest benefit with energy and supply and demand with long duration energy storage. So look forward to more questions and like to hand it over to Raj for his panel. But again, thank you for the opportunity to be here today. Raj.
Very good. Thank you, Julia. So let me just share my screen. So hopefully you can see it. So good afternoon. My name is Raj Agrawal, and I'm at BASF, responsible for marketing and business development of NAS batteries in North America, and I'm based in Houston, Texas. And thanks also to ATA for inviting me to this panel. So today I would like to talk about a mid to long duration battery storage technology, which is optimized for 5 to 8 hours of storage and has been around for almost 20 years with close to 5 gigawatt hour of installation worldwide. These batteries have been used for applications ranging from short duration, such as ancillary services, to long duration applications, integration with renewables, for example. So quick overview of BASF. BASF is one of the largest global chemical companies with a presence in more than 90 countries, and we have close to 100,000 employees. We have 240 production sites with 6 large chemical complexes. 3 of these are in the US along the Gulf Coast. BASF has about 90,000 customers and work with over 70,000 tier 1 suppliers worldwide. So as you can imagine, with large chemical companies, BASF also has a strong focus on sustainability, and our climate targets include net zero by 2050. Now, all this is important if you look from bankability point of view, right? So as we like to say that BASF has been around for 150 years with a strong balance sheet. And there's a very good chance that we'll be around for a long time to honor any performance warranty, maintenance agreements, and things like that. So quick background, a few years ago, BASF also realized that long duration energy technologies will be needed as we add more and more renewables. And we started a research program to develop long duration batteries based on sodium and sulfur chemistry. So the raw material in this case, sodium and sulfur, these are available in abundant quantity, and they're used to make many industrial materials, industrial chemicals. So we developed and tested a prototype, and then we came across NGK, which is a Japanese manufacturer of sodium sulfur batteries, who has been installing these since 2000. Now, interestingly, the technology itself was developed by Ford, Ford Motor Company in the late 60s. And there were R&D programs in US, Europe, and Japan, but battery was never deployed on a commercial scale. So in 1984, TEPCO, which is a large Japanese utility company, and NGK, they started a joint development program and spent quite a bit of work, looking at the technology and developing it, and especially the electrolyte part, and the batteries were commercialized in 2002. BASF signed a sales partnership agreement followed by a joint development agreement with NGK to further improve these batteries and to look at opportunities to reduce cost as well. So this slide basically shows the NAS battery system design. And let's see, so the third picture from the left shows our smallest battery, which is a standard 20-foot container and has 1.5 megawatt hour of energy. And the container includes ventilation, sensors, and the battery management system. Now, one of these containers, they carry 6 modules, and each module contains roughly 200 cells. Interestingly, also the space in between the cells is filled with sand, which act as a safety barrier. So I'll go in a little bit detail how it affects safety. And looking at the cell itself, it has, like any stationary storage, it has sodium anode, it has sulfur cathode, and electrolyte in this case is solid beta alumina ceramic electrolyte. Now, one interesting feature of this chemistry is the operating temperature of batteries around 300 degrees C, which is required to keep the sodium and sulfur in molten state. But as long as the battery is cycled routinely, the aux power requirement is very low because the discharge process is exothermic. So when we discharge the battery, it releases heat, which is sufficient to keep the battery at its operating temperature. And some other interesting features are, so there is no self-discharge, and the battery can be discharged 100% completely without any impact on degradation. The response time of battery is a very fast, order of milliseconds, really controlled by PCS. And the calendric life of battery is around 20 years or 7,300 cycles at 100% depth of discharge. So the 4 container system connected in series, it's shown on the right side, which has capacity of 6 megawatt hour and is optimized for, again, 5 to 8 hours of energy discharge. So this picture shows some of the installations over the last 20 years. And of course, NGK being a Japanese company, Japan has some of the largest installation. I think the largest being around 210 megawatt. Outside Japan, Abu Dhabi has one of the largest installation, which is 108 megawatt, 6 hour, and it's installed at 10 locations, but controlled centrally. Italy has a 7-hour duration, 35 megawatt installations operating since 2015. The US also has over 20 megawatt of installations. And these installations were done for many, many different use cases. So many of the earlier applications were investment deferrals or to stabilize the grid. In some cases, to supplement or replace peaker plants. Often the batteries were used for multiple applications. So for example, in Italy, they added a lot of renewable energy in south part of Italy, which created congestion and transmission bottleneck. And NAS batteries help reduce transmission congestion and deferral of investment in the new transmission lines. Same thing in Abu Dhabi, the utility company looked at investment in peaker plants to meet the occasional high load demand and eventually decided to use NAS batteries. There are many island or microgrid applications which are also quite interesting. So for example, there is one running in Catalina Island, which is just outside LA since 2011, where battery is used to balance demand and supply. And this is also an interesting case because island has 2 diesel generators. And if they run both the generators, then they produce too much power. Whereas if they run one generator, then power is not enough. So you can see this is a classical case where they run both the generators, they charge the battery, then they can shut down one generator, and they can use the battery and generator to basically supply the demand for the island. So altogether, long duration NAS batteries have been installed at over 200 locations with a total installed capacity of around 5 gigawatt hour. This slide shows the picture of 3 installations of different sizes. So the left side picture is of installation in Kyushu, Japan, and it's the actual picture is not, let's say, computer added design. The batteries were added to solve the problem of too much solar, where utility company had to suspend the connection of PV to the grid. And this project was successfully deployed in 10 months. The footprint of this project is around 100 by 140 meters, which is roughly 3 acres. And the picture on the right shows installation in Abu Dhabi, where the batteries were connected to 10 different substations ranging from 4 megawatt to 40 megawatt. But they're all controlled centrally with a centralized integrated system controller. So, very much idea about a distributed generation system. The picture on the bottom right shows one of the recent installations, which is done at a BASF chemical complex in Belgium, again, to test the different use cases for customers. This slide shows some safety tests done in Japan by various regulatory bodies, and these tests were done in around 2011-12 timeframe. But the idea here is to test the batteries under extreme abuse cases. So for example, the module was exposed to fire, short-circuited the cell, and then modules were immersed in water for several days, drop test and things like that. There was also an interesting test where cell was ignited on purpose to see what happens to the neighboring cells. And because of the sand, there was no damage to the surrounding cells. So, if you look at from safety perspective, these batteries are quite safe. And actually the modules and cells were redesigned in 2011. And since then, there has not been any safety or fire incident with about 4 million cells in the field. These batteries are in the US undergoing UL certification. So right now, cells and modules have been certified for UL 1973. And we are designing tests for 9540A, which is the thermal runaway testing for the container. So just to summarize, these batteries can be deployed in ambient temperatures ranging from -20 to 45, actually 50 degrees C. The life of battery is 20 years or 7,300 cycles at 100% depth of discharge. There is no self-discharge, and degradation is a function of discharge only. And there is really no impact of time, depth of discharge, state of discharge, temperature, C rate, these parameters, which make this chemistry quite unique. And the next generation of NAS batteries to be available soon, so that will be Q1 of next year, is expected to have less than half the lifetime degradation compared to the current design. So we expect to release that Q1 of next year. We have also started to collect some cell failure rates for the batteries which have been operating in the field. And the data shows that cell failure rate is very low, around 0.01 to 0.02% after 10 years of operation. So this, reduces also the need for augmentation. The main material used to make the cells are sodium and sulfur. These are low-cost industrial materials with a very stable pricing, so we don't see this fluctuation of pricing, and the batteries can be recycled easily. So this is all I have, and thanks for your time and attention. And let's see, I think our next presenter is Hans from Azilio. Hans, please go ahead.
Thank you very much. Let's see if I can click here on the right buttons. So, can you see my presentation in full screen?
Yes, great, thanks.
Okay, great. Well, I would say thank you for the opportunity to be here as well to talk about long duration energy storage, which is a very interesting technology, and we are definitely would like to see this happen now, because we believe that there is a big need for the in general to take the next step in renewables. So quickly then, from 1 week back, I am heading the US for Azilio as a country manager. Before that, I have been working with as a senior business developer in Latin America, Spain, and also US. So it's not as a completely new thing for me, but we have decided that we focus a little bit more on the US because we believe that there are a lot of interesting developments, especially in long duration energy storage here, and we believe that our technology can help a lot into that. So long duration energy storage is key for the renewable transition. So we actually believe that this is extremely important, and I'm happy that Julia, you represent the council, and Azilio is a proud, a proud founder of LDS. So we were there from the beginning. So we strongly believe in the same things here. The problem that we solve with LDS is, well, it's many problems, but if we try to just, many people know why it is like this. But I mean, we have a situation where we see the demand curve and the renewable production curve is not in sync in the network. So when we start to produce and more, or you have a higher penetration of renewable energy, then we come up with a situation that we actually overproduce during the day, and we have too little power in the evenings and afternoons and the evenings. And this is, I mean, there is a discussion about, or we're talking about the duck curve. We can flatten the duck curve, but we need to do more than flatten the duck curve. We need to decarbonize the night as well. So both of those things together we can actually do with the long duration energy storage. So we need to cover for the energy demand during the complete night, and I believe we can if we use this technology. In the previous session, they were asking about how much battery investments there's been doing compared to the solar, and this is the question. This is the answer. From 2020, it was only 1% of the total investment in that went into batteries, but this is now exponentially increasing, and we know that this is necessary to handle the increase in renewables. So this is something that we have seen in US as well, that the investments are increasing, and it's also we're also building knowledge about the technology as such. Long duration and short duration storage then, and I saw also in your presentation there, Julia, that the line is drawn now with 8 hours. Before we were discussing 6, 7, 8, or etc. But we can say around 8. Then we have LDS, and below 8, then we have a short duration energy storage. But this is of course not a digital borderline. We can see here that this is, shifting into the different, where you can see that the benefits increase from LDS perspective compared to the short-term and lithium-ion batteries. So, you can also think about this as if you need to create a battery situation, you can actually have a hybrid situation as well. You have for certain peaks, you can have lithium-ion batteries, but if you have, as I said before, on the 24/7 cycle, and you need to decarbonize the night, then you will definitely need a base load and a different technology. So the US leads the charge of storage deployment, and I would say it leads also the policy activities. Some other countries are also hooking up to this trend, because they also see the same need. If they want to increase the renewables as a part of their grid and the penetration of that, they also need to increase in storage. So you can see this curve is very steep, and it will need to be that steep or steeper if we're going to catch up here for the investments that are ahead of us. So what's on the policymakers' horizon then? I think that it's clearly identified that this area is very, very important, and the way to make this happen is like a little a snowball that starts rolling down the hill, but it's getting bigger and bigger and bigger. So I think that the snowball has started now, and most of the different states also recognize that this is something that is very important, and they learn about different technologies between each other. And the latest, I would say, happening on the policymakers' horizon was actually when now that the US bipartisan infrastructure law was passed, and we can see that there is a lot of funding coming into specifically long duration energy storage, and that program is called Long Duration Energy Storage for Everyone Everywhere Initiative. A lot of acronyms there, but it's good. So what we have in Aselio there, it's actually a thermal energy storage power on demand, we call it. So this pod, what it has inside is recycled aluminum, and the recycled aluminum we are heating up so it comes up to 600 degrees. And then we use the phase shift between liquid and solid to transfer this energy to a Stirling engine. And the Stirling engine can actually give, or our, if you call it the test pod battery, then it can give both heat and electricity. So this is something that you can select depending on the product that you have, and then we can go into a case by case and do analysis of what you need. So what it actually does, we take renewable energy, we charge these pods, we store it in the pods, then in aluminum, recycled aluminum, and up to 1,110 Fahrenheit, that's 600 Celsius. And when it's fully loaded, after 6 hours with 100 kilowatt loading, preferably from photovoltaics, PVs, and then we dispatch it when the demand is needed, so to say. And that we can extend that to 13 hours during the night. And that cycle it's a 24/7 cycle. So the system is designed that we should be able to do this during 30 years. So an investment here, you can think about doing this cycle, charging during the day and discharging during the night during 30 years. And after 30 years, the aluminum is still in the same shape as from the beginning. It's no degradation at all on the capacity and store the heat as the energy then. So this is a little bit how it works, and with the completing the 24-hour cycle, you have the solar, you charge it both to the demand. In this case, you see 3 houses then, but it could be an industrial compound, it could be a agro, or it could be a mining. At the same time, we have the extra power coming from the solar we use to charge the test pod. And then when we go over to the night mode or discharge mode, it doesn't have to be night, but in the afternoon, let's say if you come into the hours of a duck curve of people coming back that want to use their shower and air conditioning and television and load their cars, then it changes. Then we start and take out the energy from the storage and we put it into the demand, and then in the morning the cycle starts again. So this solution is a very sustainable solution because we have basically zero emission, and it's completely recyclable, and it's a 30-year lifetime, and all the sourcing here, I mean, most of the material is recycled aluminum, so it's already, I mean, resourced once, and we can actually, at the end of life of the product, we can sell it again. So and this, of course, is meeting the UN Sustainable Development Goals, number 7, number 9, and 13, and 11. So and then another important characteristic on the test pod is that we can actually deliver both electricity and heat. And we are looking into those segments that we have checked here. I mean, sometimes you don't need the heat, but there are many, many applications where you can actually use the heat as well in the combination. And by that, you come up to a very high round trip efficiency. So some of the segments that we have been looking into the US is the poultry farms, and there's a very big market there. We also looked into dairy farms, and there is an equally big market on that side. We have walnut producers, wineries, and all of these are basically using both. They can use both the electricity and they can use the heat component. And what in the phase that we are now, we are we have a partner called MMR in US, and what we have started with MMR is a collaboration both on the commercial side, but also on adapting the test pod from European standards to the US standard. So the UL certification will be done and run by our partners MMR in US then, and we have started that job. So that we hope that it will be some months, and then we will have a clear and certified product for the projects to be developed in the US. So what can the test pod offer for the US business then? I mean, this is reliable clean energy, and we can provide both heat and power from it. And in some areas, we know that you also have an unreliable grid, and this is a solution also to make this grid more reliable. If you want to be sure that you have energy, you can actually use this, and you put in the pod in the cluster configuration. We can also provide resilience and network for when you have weather disaster, damages, and storms, etc. What is very important for many people when they run business is also that they have a predictable and affordable energy prices. And sometimes, well, you know now what happens with the gas, diesel, and the energy prices is bouncing up and down because of the situation that we have in the world when the Ukraine war, etc. And so this is moving a lot, and it's very hard to run a business when your energy prices are going up with 30, 40, 50%, or even more in some cases. Of course, means of avoiding pollution backups and achieving sustainable targets. I mean, polluting backups like diesel generators, etc. You can actually decarbonize that quite a lot. We have cases where we had discussed 20% to start with, and when they saw the numbers, they said, "Okay, let's go 100%." They wanted a platinum PPA. So that's good, but I mean, it was based basically on economical calculations. So that is quite good start. And then, of course, distributed power offers deferral of transmission and distribution infrastructure cost. These duck curves, when this happens, and if they're getting steeper and steeper, that means that you need to have, I mean, the utilities, they need to have even better transmission and the distribution infrastructure because of the peaks. But if you use a power distributing solution in the network, that can help them a lot on how they dimension and how they defer this kind of investment in the transmission and distribution infrastructure. And last thing then, I mean, I believe we are LDES ready. As soon as we get the UL certifications, and we are ready. The question is if you are ready, but we are ready to talk projects whenever you want. Thank you very much.
Thank you, Hans. Now we'll hand it over to Marie-Pierre. Thank you very much. I hope everyone's ready because we're here. If you can stop sharing, we'll hand it over. Thank you. And please keep the Q&A coming in through the tool. That's great.
Oops, sorry, I can't find it. There it is. Okay.
Thank you, Anne. I'm going to start sharing my screen. So is it visible now? Yes? Okay.
Yes, you're great.
Thank you. So hi, everyone. Very glad to be here today. So I'm Maria Paquin. I'm a chief advisor in the office of the chief scientist for Rio Tinto. And today I would like to present the LDES, but from the demand side. So obviously we're not a long duration energy storage solution provider, but we are very much interested in technology because we have many applications for long duration energy storage across all of our business. So I will try to give you an overview of what's the business, what are our challenge, and where do we see like the hurdles to adoption of LDES, but where do we see also the opportunity in the medium to long term, and how can we accelerate the deployment? Sorry. Here we go. Okay. So about Rio Tinto, just a few words here. We're a mining company. We're present in 35 countries. We have almost 50,000 employees, 37,000 suppliers, and 2,000 customers. And what I wanted to point out on this slide mostly is that the commodity, the metal and the mineral that we produce, for the most part, are very linked to the energy transition that we're trying to achieve. So we'll obviously need copper for all the electrical infrastructure and steel to build those windmills and the rack for the solar panel and the lithium for the battery and the aluminum. We just had a good example with ants just before, so we need to produce it. So all of those elements will be required by the energy transition, but we also recognize that we'll need to be able to produce those metals and minerals with a minimum footprint. Whether it's in the greenhouse gas emission, but also on the land usage and being good steward for the water resources and providing like value for the community and leaving the land in the state that is good for the whole community. So in order to do that, it's a big challenge. We need to increase the production in most of those metals and minerals because the demand will increase, but we'll need to do it in a very sustainable and responsible way. On that slide, just to give you an idea of where we operate, and especially pointing on the US. So on the US, we have two main operations. We have the operation in Kennecott Copper in Utah, where we produce copper anodes from the mine just close by. And we have the Boron site where we produce borate in California. So those two sites are particular, and I'll try to highlight their particularity throughout the presentation. But we can say just up front that the Kennecott Copper site is, I would say, what qualify as one of our smaller big sites. So that the energy requirement for a site like Kennecott Copper is very big. So just to give you an idea of the size, Raj presented the amount of sodium battery that was installed over the last 20 years across the world. And that wouldn't be enough to power Kennecott Copper. So we would need more than what's been installed over the last 20 years across the globe, just for that site. So you would think about 5 gigawatt hour of storage that would be required. For boron, it's one of our medium size, I would say. So it's about 1.5 gigawatt hours of storage that would be required for a site like boron. And most of it is for heat, process heat. So the type of storage what we would be looking at in that type of site would be probably a combination of thermal and battery storage that would fit the requirement for such a site. So if we talk about our commitment towards the greenhouse gas emissions, in 2021, October last year, actually, we revised our targets. So we accelerate our decarbonization plan, and now we're targeting a 15% reduction in absolute emission by 2025. Previously, it was the target for 2030. And we also increase our target for 2030 to 50% of our emissions. with an goal of achieving net zero by 2050 or earlier. By doing that, we also commit to have a growth, a carbon neutral growth overall. So if we do emit from a new project, we should reduce from an existing asset to keep the growth neutral. And we also committed to work with our partners, so many our customers, to reduce our Scope 3 emissions. And in order to do that, we've committed above $7 billion in direct capital allocation between 2022 and 2030. So this is to achieve our 50% reduction target. So where does our emission come from? If we take all of our Scope 1 and 2 emissions, it accounts for a little bit more than 31 million tons per year. That's quite significant. It's a large amount of emissions. Most of it, the biggest part of our emission, is coming from our current electricity consumption. So the grid is not fully decarbonized. So we have a lot of emission coming from the electricity that we buy. There's a big chunk of it that is related to the operation of our aluminum smelter in Australia, but there is from our US operation also. So this is a mix between our purchased electricity and self-generated electricity. And that being said, we have 14 million tons of CO2 emissions just by the electricity that we consume. And we have to keep in mind that we've already had a 76% decarbonization of our grid. So if we think about all the energy that is consumed, electricity that is consumed by Rio Tinto, there's already 76% of it that is renewable. We have a lot of operation in Canada where we hook to hydropower and New Zealand. So we already have 76% of our grid decarbonized, but we still emit 14 million tons of CO2. The second big part is the anode and reductant. So when you use carbon to do a chemical reaction to reduce some of our material, so that would apply to the ilmenite smelting and the aluminum smelting with the anodes. This is more of a process emissions, and it doesn't really relate to the long duration energy storage solution. But we have very minimal of these in the US. Then in third position, we have the mobile equipment. So the diesel that we use in our trucks and our drills and all our light mobile equipment, all of that, our trains also. So this is about 4 million tons of CO2. And after that, well, actually it was before that, we had the process heat and process gas. So if we add the two of them, it's about 6.7 million tons. Mostly it's to provide heat to our process. So you can think of about alumina refinery, any kind of drying, the steam generation. These are the kind of operation that makes out the rest of our emissions. So with all of those solutions, there's different long duration energy storage that would apply. And we quickly found out as we started to get interested in that topic that there won't be one solution that would fit our needs. We'll need to be very particular about where it is in the world, what is the renewable energy coming from, and what is the usage of the electricity or the energy that we want to do. So if I give you just a bit an overview of our electricity requirement, as I said, it's 14 million tons. Most of it comes from our Australian operation, so mostly the smelter and the alumina refinery. There's about 40% that comes from our others operation across the world, aside from our iron ore operation in Australia. And that's in that category that you'll find Kennecott Copper in Utah and our boron operation in California. So it's still 40% of the electricity emissions. So our challenge, well, we cannot stop a copper smelter, we cannot stop an aluminum smelter, it doesn't work like that. So you need reliability. So if you're up to a solar or wind, you need something to compensate. So if you want to get to neutrality at some point, you cannot have diesel generator. You cannot have a backup that is using fossil fuel. You need some other solution. Integration also is a big thing. If you can think about an aluminum smelter who's drawing about 1 gigawatt of power from the grid, you cannot switch it on and off, or I'll be on the grid today, but not in an hour, etc., because you will induce instability in the grid. So you need something that will be reliable and that you can smooth the operation. And one of the other challenges, and that is not a small one, is the scale. So I pointed at it when I mentioned the battery scale. So in terms of those electricity needs, what we've identified quite early is that we'll need a solution that is more into the family of electromechanical type of storage. So the liquid air, the compressed air, the pumped hydro type of storage, because that is so much power and so much storage that using battery or thermal would be very difficult at those scale. Maybe in the future, but at this point, the maturity of the solution are not there to answer to that kind of need of like 1 gigawatt of power for a single site. Then the processing. The processing is another area that we can probably decarbonize with the help of the long duration energy storage solution. And in that type of solution, we're thinking about a combination of battery and thermal storage. Most of the heat is used to either do calcination or drying or raise steam. Currently, it's done mostly by natural gas or by burning coal. So we need to replace it by electricity in some way or shape. And that's where the storage will come in. So is it by thermal storage that can be used as heat after that, or thermal storage that can be transferred to electricity and then back to steam, or directly from heat, like solar thermal, store as heat and then use as heat. So these are all the solutions that we're considering at the moment. But again, we need reliability. We need to be able to rely 24/7 on those solutions. You cannot stop an aluminum refinery for 6 hours a day. It doesn't work like that. You lose more than 6 hours of production because you need to restart all of it. So here I'm presenting you an opening to some of the challenges that we see. So when we look at long duration energy storage, one of the main challenge for the industry, and I'm being very transparent, is the cost of the electricity that will be consumed at the end of the day. So here I refer to the cost of the levelized cost of electricity stored. So after you recover it from the storage. So what are the key factors that will impact the cost that of the electricity that you will use? That will also apply to the heat if you were to use the heat. But the electricity price is a big thing, but it's not the biggest thing that can impact the final cost of the electricity that you can use at the end. The capex that you need to put in the storage is a bigger factor, and the average discharge rate also will play a big role. So the average discharge rate will be greatly influenced by the percentage of the electricity that you want to compensate by renewables. So if you're targeting, as Julia was mentioning at the beginning, like over 80%, you'll get to silver and then to gold and to platinum. So going from gold to platinum will decrease your discharge percentage, and then will have a very big influence on the final cost of electricity. So these are all things to be considered, not only the price of electricity. So on that side, what you can see is what will be the cost with different energy costs coming in your storage for 18-hour storage at 75% discharge, and 18 hours storage with 50% discharge. So you would see with a very low price of 0.5 cents per kilowatt hour, you get to well, if I put it in megawatt hours, about $125 per megawatt hour. So you start by $5 and you end up at $125. So even if you have access to very cheap electricity, at the end of the day, when you're firming the electricity, the cost is very impressive at the end. So this is one of the big challenges for the industry. How can we minimize that cost? By playing on the lever that we can play on. So then I come to the hurdle and the opportunity. So hurdle, I touch a little bit across the presentation, but the high capex is obviously one that is of concern at the moment. And we're looking around all sorts of solutions. How can we decrease the capex? The coverage, as we approach 100% or the gold, the platinum standard, then it becomes much more expensive because we get to a lower discharge percentage. So how can we go around that? And the limited demonstration of the technology at the scale that is required by the industry. So when I'm talking about the amount of megawatt or gigawatts that will be required by the mining industry, you can apply that to the steel industry or the cement industry. That would be similar scale. And the low round trip efficiency that we can see right now, especially for the large scale solutions like a pump hydro or liquid air storage of comfort, etc. But there's opportunity also. So it's not all dark. There's we see that we can influence, and there's potential solution on the horizon. So Julie mentioned the long duration energy storage console, and they've been very helpful for us to have maybe a longer term view on those solutions. And the capex for these kind of storage could be decreasing by 55 to 60% by 2040. So this is major. This will have a tremendous impact on the final cost of electricity. And there's the other one is, I don't want to let perfect be in the way of good or better. So we shouldn't stop ourselves because going 100% renewable is too expensive. If we can get to 90% or if we can get to 95%, that's already a big step, and we should do that. And maybe wait a little bit later when the cost is going down to go the full way ahead. The target being to be net zero, obviously, at the end, but we should start. We shouldn't wait till it's perfect to start. There's also a lot of opportunity right now to help the development of those solutions and in piloting and doing, because right now we still have all the backup. We have the genset, we have the power grid that is still not clean, but it's still there. So we have the opportunity to pilot with minimal risk in our industry. So that's the time to influence and to help the development. Also, the round trip efficiency, we expect to see gains in the future by 10 to 15%. That will also play an important role in the final cost of the electricity. And one thing that we're looking very closely at is what kind of grid service and operation practice could we use to lower the levelized cost of electricity at the end of the day. So at the moment, we're currently providing some grid service with our assets. You can imagine a smelter with 1 gigawatt of power requirement will have an impact on the grid, whatever the grid it is. It's big enough to have an influence. So we can help stabilize the grid with those assets. So how can this help the integration of more renewable more quickly? That could be one solution. When we get to the long duration energy storage solution, where should we put it? Where's the best place to integrate those solutions into the network to make the best for the grid? So is it behind the meter? Is it on the grid side? Is it that hub specific somewhere? Where is it the best place for us to do that? And if we can get some revenue from providing grid services, again, it helps us justify the integration to our operations. On the operation practice, there's a lot that can be done. I mentioned that you cannot really stop an aluminum smelter. That's the reality. But we might be able to lower the production for a few hours by a few percent. And that small wiggle room that we can find might be enough to compensate the fact that we're not able to go to 100% with the long duration energy storage. So there's a lot of optimizing that should go into what's the best mix of solution. What is the best size of long duration energy storage that can be compensated with operational practice that can lead to a full decarbonization of the grid. And there's probably a sweet spot that we need to find in the future. So that's what I add. I think I give it back to Julia now.
Thank you, Marie-Pierre. I mean, this was a fantastic conversation. As you can see, when we're talking about long duration energy storage, we can talk for hours and days and months. So we could keep going, but we want to be respectful of all the other panelists and appreciate the questions that came in and to the panelists to answer them on the spot. So that was great. But as you heard the themes of sustainability and, we've already meeting a lot of targets now, just, the important role of long duration energy storage and how much the costs have already come down and need to continue to come down. So, and just the map that Raj showed of, we've already have projects around the world. It's pretty exciting. So, and what Hans is doing, like, there's just so many wonderful aspects. So it's great to have the different perspectives. And again, thank you all for your time, and I'll hand it back to Carlos.
Thank you very much, Julia, for being here with us. And thank you, Hans, Marie-Pierre, and Rash, for your presentations, all very insightful. I think we're going to go to the next session now. Please stay with us if you can, and ask questions and interact with everybody else on the chat. So thank you very much for being with us. So for those of you who are in the audience, stay with us, and we're just going to share my screen so you can see who is up next. We're going to be talking about financing. So right, so as you can see here, we're going to be talking about merchant project financing, PPAs, and the latest trends and financing your energy storage projects in the US. So now this session breaks the mold a little bit. We're not going to have presentation slides, but we'll have more of an interactive discussion. I'll be, just the one like steering the discussion, but the guys who know are these three guys you can see on screen now. So John O'Brien, Senior Director at Private Energy Partners, also Miguel Telechea from Mazars, and Andrew Chen from CIT Bank. So, right, I think, Andrew is joining by phone. So, as always, I'll ask the three of you to introduce yourselves and tell us who you are. But to start with, just like to ask you, how are you today? John, Jose, Andrew.
Yeah, I guess I'll start. John O'Brien at Private Energy Partners. We're the development arm of Quinbrook Infrastructure Partners. So ultimately, my goal is to help integrate batteries across the portfolio of the Quinbrook companies and investments. And I've been there since the beginning of March, and prior to that, I spent 14 years at Siemens Financial Services, and responsible for a lot of project financings, thermal and renewable. But in the last 5 years prior to leaving, it was a lot of the focus was on batteries and understanding the technology, the markets, and kind of structuring a solid financing to kind of get the more difficult transactions done.
Thank you very much, John. And Jose, so tell us a little bit about yourself.
Thank you, Carlos. Jose Telechea. I'm an associate director here at Mazars in New York. And basically, I focused on helping any player in the renewable energy and storage and overall infrastructure space with anything that has to do with their financial model needs, from audit to building to training. So we offer quite a variety of services, and just like John, I just recently joined Mazars, and before that, I worked over 11 years in the financing of renewable energy and storage projects, and I'm happy to join both John and Andrew, whom I had the pleasure of working with both of them. With Andrew and the Siemens team too, the first financing of an energy storage project a couple of years ago, and with John more recently, just before he left, we were working on what ended up being what we think is the first financed fully merchant battery project. So excited to be here, and as always, appreciate the invite and looking forward to our conversation today.
Thank you very much, Jose. And Andrew, tell us a little bit about yourself. No, we can't see you, but hopefully, yeah, there we go. We can see you now. We can't hear you yet, but I think you're on mute. There we go. Now we can hear you.
Okay, hi. Andrew Chen with CIT, First Citizen Bank. Thanks for the invite, and really appreciate it. Been in the energy markets for probably about 25 years in banking. And so, as Jose and John mentioned, we did several financings with both of them, and in both solar and wind, and now battery storage. So pretty excited to discuss the opportunities. Did financings for on the contracted side, as well as more recently more merchant type financings. So happy to be here.
Brilliant. Thank you very much, Andrew, for being here with us today. So I'm going to stop sharing my screen so we can, so they can see us. Right, so, right now, so you've been in the industry for a long time, and you obviously know the energy storage market really well. So a developer comes to you with an energy storage project, and what kind of conditions are they likely to find, and how are those conditions different to, well, let's say, last year when we spoke? I think we had the three of us were actually here last year or 2 years ago, actually, and we had a similar conversation. So how have things changed in the last 12 months, finance-wise, for energy storage projects? Maybe I'll let John start.
Yeah, I don't think they've necessarily changed all too much. Coming from the banking side to more of the other side of the ledger, I can actually find out who I was competing against, and I still think the market is fairly small on the lending side, and I don't think you'll get too much movement on merchant financings or somewhat merchant financings until more banks kind of come into the market. So think the banks that are there, Siemens, CIT, KeyBank, they all have their own view of how to structure this, and a lot of it is very similar, and there hasn't been a ton of movement in kind of changing those terms.
What are your thoughts, Jose?
I would add, because probably people are thinking, what are those conditions that we've been seeing in these projects? So you can probably expect tenor somewhere around the 5 to 7 year mark, more or less. And I mean, I'll let Andrew, who's still a banker here, correct me if I'm wrong on anything that I say. But I think overall, like John mentions, there's still not a big group of banks that are comfortable, because storage is to say the least, much more complex. So and you're probably gonna see prices that are gonna be very dependent on the actual structure and the actual specifics of each deal. So it's hard to give a range. The more merchant component, of course, the higher the prices. But there's definitely a trend, just because of the overall interest rates in the world going up, that the cost of financing is also going up. So that's something that I think there's already been a couple of sessions today in which this has been mentioned, and the costs are increasing overall, and that's making some of the deals that were profitable maybe not profitable anymore. So it's an interesting stage that we're at, but I think there's a few players, just like CIT, Siemens, the NatBank who I worked for, etc., that are willing to finance these projects. But it's definitely, you know, not a plain vanilla financing, and there's a lot of things that need to be taken into account. You can expect cash sweeps in the structures if things don't go as expected. You can expect higher DSCRs, probably DSCRs of at least 2.0. So that's kind of the overall terms that you can expect. And I'll let Andrew take and maybe correct me on any of the points that I just mentioned.
No, I agree, Jose. I think a lot of the differences between maybe a year ago to now is there's definitely a bit more liquidity. But that being said, the ones that are more structurally conservative would probably get financed versus the ones that are super aggressive. That being said, there have been quite a few financings out there with 100% merchant type arrangements where don't know if it necessarily has closed, but there's definitely a lot of traction and banks are taking a look at them. Just because, I think from a banking standpoint, there's tremendous liquidity still in the market, and the ESG component is a big plus where there's a big push for more ESG, battery storage, solar, wind. There's just a tremendous amount of liquidity. So that being said, overall with the liquidity issue, but you also have the supply chain issue. So, and with costs increasing because of the supply chain issues and just in general inflation, you are seeing less, deal flow starting to scale back a little bit. But overall, I think this is the market is still very robust, and I think there will be many more opportunities coming down the pike, and especially if the supply chain issues start to resolve. I think that would be a big help to provide more financing.
Thank you very much, Andrew, and building up on what you've been saying, and what a few of the panelists have been saying today in other sessions. It's clear that in most cases you can't really build a case on one service for energy storage, be it because maybe that service is profitable today, but you don't know what's going to happen down the line, or because quite simply just the numbers don't add up. You need to provide a few services. So typically, what are those services that you look for that energy storage projects can provide, so they can be profitable, and you think of a project as a good project? So just to clarify the question, so what are the services that attractive energy storage projects provide from a financial point of view? What are the mix of services that makes the project bankable?
Yeah, I think it's very market dependent on what's payable. You can look at the PJM market, and that's really frequency. Then you can go to California, and then there's certainly some reg up, reg down. ERCOT, it's RRS, which is essentially spinning reserve. But all those markets are very thin, right? It doesn't take a lot, even with a huge addition of renewables. You're probably not going to be adding that many more megawatts that you need for a lot of those ancillary type services. So what you have to look for then is kind of where your location of your project is. So there isn't right now a lot of other products, some very thinly traded, thin megawatt ancillary markets. And then it's all driven by location and what can you get extra. So California has such a large number of projects because the RA component really is beneficial to bring you over that hump. Texas, it's big because you can just really do anything in Texas. So I don't know if they're economic or not, but they're easy to get done. So if you want to get a pipeline going, Texas is a place where you can do it. And then, then you start looking at the other projects, which are, scattered across the country, whether it's New York or kind of the Southwest. There's a lot of tolling agreements. The utilities can monetize that better themselves with their responsibilities. New York with the VDER stack. So, then there's some other RFP areas as well. So, but right now, merchant-wise, competitive wholesale market-wise, based on when your project is going to come online, if you start building it today, you really need to have a very premium location to do energy arbitrage and then backfill with some of the ancillary products.
Right. So essentially, you're trying to place your storage project in a place where you could get a big spread of prices between, and that's what makes it more viable, primarily viable, right? So would you agree with that, Andrew and Jose?
Yeah, I think so. I think with the most of these battery storage opportunities, as John was saying, is probably trying to benefit off of the energy arbitrage. As we saw here in Texas with the Uri storm, there was some significant displacement in prices due to the snowstorm, and unfortunately there wasn't enough battery capacity to be able to be discharged. And so I think now the general sentiment is, as the costs start to come down on batteries, it's a short construction cycle, and you're also looking at once you get this in place, you'll have the opportunity to deploy when the pricing environment gets fairly high. So I think from an equity standpoint, this could be a home run in certain instances. You could have almost a couple hours that you could make up, several months or even years worth of revenue. So that's why there's definitely value to these battery storage opportunities. However, if the pricing regime, the market prices were to remain fairly steady, then the issue would be it would not be as lucrative. And so I think there's this interplay that's happening where people are building it. If they build it, people will come, but it might come in short durations. But those shortages that happen could be very, very lucrative. So I think that's where a lot of people are putting the investment. And it's not like a gas-fired power plant where it's going to take a 2-year construction cycle. It could be 4 to 6 months of just installation. So that's what's also very appealing to the battery storage space.
Right. Jose.
I would just add, I think, as it has been mentioned, storage is so unique because it really comes down almost to the project level, and I think that's why it's becoming a little more. It's taking more time than expected, maybe to see more lenders in the space. Even though there's so many developers, it's because it's pretty complex and it's pretty unique. As John was mentioning, it really depends on the market and the actual location of the projects to which revenue streams you can profit from. You have several, and then you have, for example, in California, several that you can monetize, whereas in other markets, you cannot monetize those ancillary services yet. So I think there's a lot also driven by policy. So you'll see, some of these projects being driven by actual, RFPs by utilities or just, maybe state level requirements. But it really depends on, who you are, taking the word from, because I think what I've seen in the space is that everybody has kind of their own view. There's different market forecasters. There's different, players that are seeing the different revenue streams differently. So while you can have one location in which one company or one consultant or one person can believe it's gonna be a lot of revenue from energy arbitrage, you might have someone looking at the exact same project and believe that it's going to make more money out of ancillary services by itself. So it's really, you know, it's really unique in that sense, and it's a challenge. I think, you know, at the end of the day, everybody has their own view, but there's definitely a case to be made, and that's why I think there's so many projects in the pipeline. There's an economic sense, an economic reason to build these projects, regardless of what your revenue source is. And I do think there's one more point that I would stress is that I think there's a shared view that the ancillary services will, you know, their value will diminish throughout time just as more battery projects come along. You know, so for now, projects that are ready to be built or soon to be built are probably gonna look at better years in terms of revenues than those that are, you know, looking into further years down the road to be finished. There is this downward trend to, you know, to the ancillary services revenues. And if you add to that, maybe even on the resource adequacy, which is usually a big component of these projects, at least maybe 30% on the overall revenues. If you add an increasing duration requirement that might come along at some point, you know, that also factors into your numbers. So I think there's a lot of considerations, but at the end of the day, it's still profitable in many specific instances, and that's why we're seeing so many projects.
Right. So, you know, one of the things that you mentioned, Jose, and it's been, you know, mentioned a few times throughout the whole session, the whole workshop, is that with ancillary services and probably with like arbitrage opportunities as well, the more batteries that are deployed in like one particular like node or a place, you know, that the opportunity decreases. So where are we now? You know, are we still like early days where there is lots of opportunity for like players who want to come in and invest, or is it already a market where people need to look carefully at, you know, not you know, getting too late into the market and getting themselves into a situation where it's hard to make a return of the services they're providing?
I mean, I think it's been a lot of it's been looked over, and you can just take a look at the queues that there are a lot of sites, especially in the prime markets, so California, but especially Texas, of the amount of megawatts that are online. And then what you got to take a look at, if you're, you know, building a project, and Jose really meant, you know, you take more time to think about this, which is the duration of the project. So, you know, the standard frequency project, in and out, easy, cheaper battery at 1 megawatt. But if it's going to be you know, if you're going to try and clip 2 peaks, you know, 2 hours of the peak, you know, a 2-hour battery makes more sense. That's a little bit more future proof. And then, you know, you look at California, or, you know, California and New York, you know, where you're going to need to have 4 to 6 hours of your battery. That's also plays into your thoughts today. But it also depends on, are you going to have a persistent duck curve that you can pick off, or is it going to be singular 15-minute spikes? You know, and that also plays into it. So if it's going to be, you know, really quick spikes that you want to take advantage of, that's a 1-hour battery. But if you have a persistent duck curve, then maybe you'll shift to a 2 or a 4. So it's all very node dependent, but I think a lot of people have been looking for a while at good sites, and it's just evidenced by the huge number of megawatts in the queues.
I think also to further that, you know, the responses, you know, where are we in the cycle? I think it's we're still kind of in the mid-stage build out is my guess right now. Is, you know, probably just like maybe 3 years ago. You know, 3 to 5 years ago was probably when maybe the first few battery storage projects were actually fighting us. And now you're looking at, you know, when the first one was done, we did one, I think 4 or 5 years ago, and it was 100% contracted. Pretty straightforward. It was behind the meter. Now you're looking at quite a few different, mostly merchant, but the build out is pretty significant. A lot of the developers are definitely asking for longer tenors. They want to see 8, maybe even longer type financings with amortizations that are even beyond that. And those are all going to be subject to independent engineers, validating the useful life of the batteries. But overall, you are definitely seeing more traction in the space. It's really exciting to see a lot more people getting involved in the space to really, I don't foresee battery storage as being any sort of baseload type of power source at all, but it would be very complementary to this intermittency that's really playing out with the wind and solar. Wind is more mature now, but solar is really starting to ramp up significantly, especially here in Texas. So you are definitely seeing complementary battery storage because what's the alternative? The alternative is really building a gas-fired peaker, and these gas-fired peakers are going to take a year or two to actually construct, and it just doesn't necessarily make it very feasible in today's market, whereas batteries can be deployed very quickly and efficiently.
And I think the other thing too, Andrew, is that there's a lot of opportunity that hasn't been exploited yet. A lot of non-wires, alternative type structures, more creative, time-certain PPAs, where as you go into scope 2 type emissions, that becomes a bit more important to kind of match up your timing. Resiliencies at whether they're data centers or manufacturing facilities that need more power. There's a lot of non-wholesale type activities out there that we could use, right? That ultimately, I think we mentioned this in our panel, in our prep, what really kept a lot of solar and wind going. And, they frankly didn't have to have these conversations of, can you do a merchant solar project, is because, right, it's a power source, and you could do the CNI PPAs that kind of matched up to what they were facing, and essentially hedging off their retail power with the benefit of green credits. You don't really have that in storage until either the green credits become a bit more strict or there becomes a value placed on resiliency. But once that comes, there's a whole nother leg that will occur. So you can argue that it's mid-stage in some locations that have a real a good wholesale market for storage, but then there's a lot of opportunities still there that's just a little bit further afield, that just hasn't been developed yet by the markets or the customers.
So, I think a related question is, right now, most of the projects you see are lithium ion, and lithium ion has like certain characteristics. It's quite like short term, quick response, so it's good for that type of service. So, when and if and when do you see other technologies being financed and perhaps to provide longer duration services?
I think this is a question that usually comes up in any storage conversation, and again, just as the storage sector overall, it really comes down to the use case and the specific project that you want to develop and the need. But I think after developing and financing this type of projects, and discussing with John, Andrew, and other people in the sector, I think for now it's already complex. So adding the technology component risk is something that's very challenging. So in the very short term, I think it's gonna be hard to see for example, just senior lending to this type of longer duration technologies, and with the lack of senior debt for this type of projects, it's gonna probably take a little longer for that specific long duration sector to grow. there might be a use case for sure. But I also think that for now, the lithium-ion technologies, if you really need 8 hours, you can put two 4-hour batteries and still get those 8-hour durations, and probably depending on the technology you're comparing it to, it's still cheaper than that 8-hour long-term duration technology. So it's challenging. I think talking about long-term is something we need to start doing now, but I think it's still something that is going to take a while for us to start seeing materialize into kind of a utility scale level. I don't know if John and Andrew agree or not with that.
Yeah, I think so. I think when as a lender, senior secured lender, you definitely don't want to take any sort of technology risk. And even when lithium ion started to unfold, I think what really helped drive acceptance of it was frankly electric vehicles, where you saw it being deployed in Teslas and other battery vehicles. And I think when we see this deployment, then we kind of slowly incorporate it into like a utility scale BESS system. And so I think without that type of acceptance, I don't think it would have moved forward as quickly. And with all the other technologies out there being discussed with more duration and whatnot, I mean, the costs are still a little bit uncertain. The ability to deploy it on a utility scale, large scale basis, it's always going to be a big question mark. And until someone builds one and we can see this see the performance, the operating performance, where it could store a charge for 8-10 hours or whatnot, I don't think anyone would be raising their hands to finance any of this.
And I think too, Andrew, right, that a lot of the comfort with lithium ion comes from the warranty. I mean, people may say that they're comfortable with lithium ion technology, but the reality is that they just look to people, especially lenders, look to the warranty and said, year 15, I should have this much output. And I'm backed by, some big companies, whether it's SK or LG or Samsung or CATL, whereas you don't have that kind of security at all with long-term, long duration storage at this point. So I think that's going to be a huge hurdle for them to overcome.
Right. So that's a good point, actually. So, what if you got, a newer technology, not necessarily longer duration, but it had a similar kind of warranty with that still like lower the risk, and make like lenders more likely to give it a chance, or still you'd really need to see, track record of a technology before like this type of commercial lending is more viable?
Yeah, I think
go ahead, John.
I would just say, I think New Energy Risk had a insurance product out kind of backing the performance of flow batteries, and that it all flows together, so that there may not be a real opportunity for a flow battery today, but no one really has financed a flow battery on the debt side, at least, using a risk product.
Right. Andrew, sorry, you were going to say something.
Yeah, no, I would agree with John that unless it's like backed by a large international conglomerate like a Samsung or some large entity that has real financial wherewithal, even at that, having a risk product like an insurance wrap or something, it may not be sufficient to get it financed.
Right. I think we have a few minutes left, and there is a question here on the Q&A box that perhaps we could take. Is by Gordon Bayer, and he asks, to John O'Brien, what would be the maximum of your investment per site? Is PEP able to finance up to 1 gigawatt battery energy storage systems when it is already in the queue in Arizona?
I can't really talk to investment parameters too much without at this point. I think in general, we'll leave what is financeable at that level to Andrew, but yeah, we'll leave it there since I am not regulated.
Right.
If John's willing to put in equity, I'm sure we can accommodate and probably put in. If he's willing to put in 50 cents, we might put in 50 cents.
All right. Well, there you go, Gordon. That's your answer. So, we have talked a lot about all the good things that you want to see in an energy storage project. So you want to see a technology that has track record at this stage that is lithium ion. You want to see a strong business case, wherever it is that you want to see a project that is deployed somewhere that it makes sense, that is providing services that are required in that particular market where it plays. It could be, if it's a complete a merchant project, a nice spread of prices. For the people who are there in the audience, what are some of the red flags that you don't want to see in a project? And you could take the opposite of those two. So lack of track record, which adds technology risk, and but what are some of the others?
Anything that has Bitcoin mining in it.
And do you see?
Yeah, we're seeing quite a few where Bitcoin miners are requiring this tremendous amount of power needs, and not to say that it's not warranted, but it's definitely on a credit quality wise, it's difficult to finance. I think that would have to be something that's more done on an equity basis. But I would say, but it is significant, and it's a fairly large market. So similar to what I think John had said previously, these offtake arrangements, maybe data centers or someone else might be a bit better candidate from a credit standpoint. But I would say, with Bitcoin miners as an offtake, it's going to be very, very challenging for the time being.
I would say that regardless of some of the red flags that can come up in these projects, there's also ways to mitigate those risks. I mean, probably not the Bitcoin miners, but I think overall there's quite a few things, and I think the lenders that are in the space are willing to actually look at those transactions in depth and find ways to mitigate the risk. But I think, for example, one of the things that John mentioned that is key is the warranties and the details in the warranties. I don't think there's a complete standardization, so they do vary sometimes in between projects, even though they're using maybe the same equipment. There's a few clauses that might change. So and that might be some red flags for someone, and maybe not big red flags for others. But there's definitely things that need to be considered and ways to mitigate those risks. So to the extent where you can find mitigation measures, I think you have a possibility of taking your project to the finish line, which is the overall goal. So and I'll take advantage here and just make that brief add on our services. So I think the all of these considerations are usually reflected on the financial models, and I think because the market is so competitive, you really need to have a tool that allows you to really make decisions and analyze all the variables that you're putting into these projects. And so if anybody has after this conference wants to reach out to me for any question overall of the sector or modeling or lending, I'm happy to follow up directly with them. I know again, Andrew and John are also great people that are always open to chatting with people, so I've really enjoyed working with them and doing panels with them. Again, I think this is a great sector, and I think there's ways to go around those red flags that you mentioned, Carlos. But it's sometimes it really has to come to putting all the people down together in a table and sitting down and figuring out how to do it.
Yeah, I mean, I think, you know, experienced people like Andrew and the other banks that have done the storage, they know who the players are. They know who the appropriate people that that you want to work with, whether it's on the battery or the construction side or the software side, and they will work together to help improve your project. What I always found a red flag, and I would always just say, have fun talking to someone else, would be if you start pushing back on a lot of my terms, then that's a red flag to me. You know, because there's a lot of experience across the table, almost as much of a developer at this point. And to push back on a lot of the terms that were just really meant to cover off the large amount of risk being taken by the lenders, that was always a red flag, because it is a partnership for the next 5 to 7 years, depending on how your project is structured. So to me, that was more than technology, because that could be filtered out quickly, and that's almost binary. The red flag would be how is being handled during negotiations.
And I'll jump real quick on that for 1 second and say, because that's very important. Those pushbacks that John is talking about, I think, there's a few people that have gotten some experience. And if you have access to those people, I would say listen to them, because all you do is delay the projects and you end up probably where you started, maybe 10 months later with much more legal fees, much more consulting fees, and pretty much very close to where you started. So I would say it's a partnership usually for these projects. So if someone is recommending to have certain clauses or certain guarantees or certain things, it's because they're needed. And so I would just recommend to really think about, pushing back on things that are being suggested before actually doing it.
Brilliant. Well, John, Jose, Andrew, thank you very much for these chat. I think, well, we have a couple of minutes, and in those 2 minutes, I'd like to ask you to just let us know, what do you see coming up in, let's say, the next 5 years in this field? How do you see things evolving? But not all at the same time.
Go ahead, John.
I just think for the next year, I think things will be very stagnant, because we're looking at around a year and a half lead time from everyone I've talked to on the equipment side, from kind of NTP to COD. So I think there might be some stagnation, and clearly, hybrid is where it's going. And there'll be some backfill, obviously, on standalone. And then I think what you'll look towards the edges in year 5 is, what new products in the market are available, and how things are getting valued. So, hopefully a lot more batteries and gigafactories will come online to make the batteries cheaper, and then opening it up to different products than we see today. And we won't just be talking about ancillary services.
Brilliant. Andrew, please.
I think the same. I agree with John and a lot of what he said, and I would say that as hopefully costs of lithium will start to come down. Unfortunately, it's going the other direction. So if that continues to rise and other costs go, we could see a situation where maybe you're right. These other technologies start to become more economic. So it's a very interesting spot to be, where maybe lithium ion won't be the surviving entity, and there'll be other sorts of technology. So, and that's probably a good thing, because then there'll be more innovation in the space. So hopefully, and obviously we're a little bit lagging in as a lender, right? We would always look at things whenever they're more mature. So we would come in with the money as things start to become more known, and and is more financeable, because it could be applied.
Thank you, Andrew. Jose, what are your thoughts on this?
No, I think I agree with both John and Andrew. And the only thing I would add is that I do feel that even with the challenges and the delays and everything that we'll see in these probably 12 or 18 months, and then, as John mentioned, maybe new technologies coming in 5 years, or the economics changing for some of the technologies, etc. I do think the storage sector is going to keep growing. It's going to keep being a key driver. It's going to still be exponentially growing. So I think, anyone that's listening to this is probably not wrong in looking into this, because I think it has great potential. I think it's needed. ESG requirements, cleaner energy requirements, etc. We will need storage in a certain way. Technology-wise, who knows? But we will need the storage, and we'll see it keep growing with or without the challenges that it's currently facing.
Jose, thank you very much. Andrew, John, always, a pleasure listening to you. And well, let's finish on that note, which is a positive note. Yeah, thank you. Stay with us if you will for our next session. And yeah, thank you for being with us today. To everybody else in the audience, I would like to ask you to stay on. We have the closing session of today's panel, which today's workshop, which is this one, which you'll see now on screen. So thank you very much, John, Jose, and Andrew.
Thank you.
Thank you.
Thanks. Bye. Right. So, well, to finish on a high note, I'd like to welcome Joseph Rand, who will be talking about permitting strategies. So welcome, Joseph.
Thanks very much for inviting me. Should I go ahead and share my screen?
Yeah, let me stop sharing my screen. And yeah, could you introduce yourself briefly as well? So, those who will know who you are, and then, yeah, you can get started with your presentation.
Very good. So thanks for having me, and I'm looking forward to speaking to this group. So I'm Joe Rand at Lawrence Berkeley National Laboratory. I'm a senior scientific engineering associate. I do a wide range of research on renewable energy cost, kind of deployment and market trends. And so this presentation that I'm going to share today is really focusing on one aspect of permitting. I know this kind of session topic is focused on permitting, but I'm really going to be focused on interconnection and what we're seeing in terms of the types of projects that are lined up in transmission interconnection queues. In other words, seeking to connect to the grid system. So I'll focus a little bit more broadly on kind of the clean energy development landscape beyond just storage, but the focus will be primarily on storage. But I do think that kind of expanding the view to see this broader landscape will be interesting and useful information for this audience too. And just as a quick background, my team at Berkeley Lab has been collecting and compiling these data from interconnection queues for quite a number of years, but we're really seeing a whole lot more interest and urgency around understanding what's going on with interconnection of clean energy in the United States. And I think that urgency is primarily growing because project developers, whether they're trying to build wind, solar, or storage projects, frequently cite interconnection backlogs and barriers as one of the leading kind of problems or barriers they face to getting their projects really built and completed in a timely and financially feasible fashion. So with the next few slides, I'll share some big picture trends that we're seeing among storage and hybrid projects and other projects that are currently seeking to connect to the grid system in the United States. But first, I just wanted to quickly highlight the Energy Storage Center that is at Lawrence Berkeley National Lab. In fact, we have over 200 researchers here at Berkeley Lab that are working on all aspects of energy storage, from electrochemistry all the way down to kind of the markets and analysis and policy that I work more on. And you can learn more about all of those efforts and initiatives at energystorage.lbl.gov. So before I really dive in, I just wanted to provide a quick primer on the interconnection process for utility scale generation and storage. Now, probably a lot of people here on this webinar already understand how interconnection works and what the interconnection queues are, but this quick kind of diagram might just bring everyone to the same level playing field. So in a typical process, you have a developer of the project that would submit an interconnection request and therefore enter the interconnection queue to begin kind of a series of interconnection studies. And those studies are designed to establish what transmission upgrades would be required in order for that generation or storage asset to connect to the grid at that point. That process also assigns the costs of those upgrades. And those studies would typically culminate in an interconnection agreement, which is a contract between like the transmission owner or balancing authority and the storage or generation owner. Now, what we've found in our analysis is that most projects that enter these interconnection queues and submit a request to connect to the grid actually end up withdrawing at some point. We need to better understand what are the reasons for withdrawal and what are kind of the drivers and primary causes for all these projects to be withdrawing rather than actually reaching commercial operations. But ideally, at some point, some of these projects do go on to be built and reach commercial operations. So in terms of what we're finding in the interconnection queues, I will first talk about projects that are active in the queues. A little bit later, I'll share some analysis we've done on projects that were completed or built, and also some analysis on projects that were withdrawn from the queues. So we did analyze about 8,000 proposed projects that are actively seeking to connect to the grid in the United States. Those 8,000 projects represent about 1 terawatt of generation capacity and about 400 gigawatts of storage capacity. So quite a monumental amount of new capacity that's seeking to be built in the United States. Now, what does that look like? So this figure shows a time series of the capacity in the queues broken out by different generation and storage types. You can see, so obviously solar, storage, wind, gas, nuclear, coal. Really there are 4 dominant resources in the queues in the United States. Nuclear, coal, and anything else is really not much to speak of. You do see just dramatic growth in the amount of capacity being proposed for both solar and storage, whereas wind has been a little bit more steady in recent years and gas is declining pretty rapidly. Now, I will also note that the hashed portion of each bar represents the capacity that's in hybrid configurations. I know some previous speakers have talked about hybrids, but it's really clear from these data that hybrids really are in the United States the power plant of the future. For example, just looking at the storage bar, roughly half of the capacity of the storage capacity in United States interconnection queues are paired with some kind of generator. So most of that actually is solar plus storage, but the capacity shown in this blue bar, for example, is only the storage capacity. So it's pretty remarkable. We have over 400 gigawatts of storage in the queues today. I will also note, I know you all have talked a little bit about different types of storage today. Really what we see in the queues is primarily lithium-ion battery, but we do see some examples of other alternatives like pumped storage or pumped hydro or compressed air and things like that. Now, we'll also look at these data a little bit by region. So across the bars, the top bar, each of these different panels that I'm showing represents a different independent system operator or transmission operator in the United States. The West and the Southeast are kind of large regions made up of a bunch of individual utilities that are not organized in a single wholesale electricity market. But all the others represent kind of broad geographic regions, and I'll show these on a map in a little while. But again, just to point out, if you look kind of year over year from 2014 to 21, just a dramatic growth in the total capacity that we're seeing in the queues, and especially among resources like solar and storage. And here again, I've broken out the storage into standalone storage and hybrid storage components. So you see, just for example, like in the West, the majority of the storage we see being proposed is paired with solar, actually. And similarly in California ISO, where again, about half of the storage in the queues is in hybrid configuration. Now, just to zoom out, one last thing to point out on this slide is the all regions on the far right, which kind of sums up all of the capacity of all these different regions and really just shows kind of that year-over-year growth that we're seeing in the interconnection queues. And this is why we hear developers of projects complaining that the queues are very backlogged and interconnection has become a real barrier. When you see this amount of volume, this growth in the queues, the interconnection process wasn't designed to handle that much volume. And finally, just to put it all in perspective, just in a different format, in this figure, I'm showing the total existing capacity for 2010 and 2021, meaning that's what's built and operational in the United States. That's over here on the left. And on the right-hand side, these two bars, I'm showing what's existing in the interconnection queues, again, in 2010 and 2021. And what's, I think, most remarkable is that as of the end of 2021, we have more capacity in the queues seeking grid interconnection in the United States than we have operational power plants providing power in the US. And moreover, if you look at the types of generation and storage that we see in the queues, it just represents an absolute revolution in the type or in the way in which electricity will be generated, stored, and transmitted in the United States compared to how it is today. So I do think we're looking at what I'd call a rapid and revolutionary energy transition occurring, and the data are right there in the queues. We also produced a series of maps to illustrate where these projects are being proposed. Again, for this audience, maybe storage is most interesting. And you can really see pretty clearly that the total for storage capacity in the queues, it's really dominated by the Western regions of the United States. The West kind of non-ISO, meaning all these utilities that are kind of not part of an organized wholesale electricity market have a whole lot of capacity for storage, but really California ISO is the dominant market in the United States. And I know you had Alex Morris from the California Energy Storage Alliance on earlier talking about kind of the market in California and the drivers there. Now, we also looked at the data at the state level. So just zooming in again, just for storage, this also really helps kind of stand out. Just again, that California is really the dominant market in the US, but Arizona and Texas are also pretty strong markets and in terms of what we're seeing in the interconnection queues. And finally, we looked at the same for county level. And so this is getting into kind of a very detailed level, but what we do see is there is actually a remarkable level of interest in standalone storage. Now, we didn't have county level data for hybrid storage projects, unfortunately, but just even looking at standalone storage, again, we see a pretty remarkable and widespread amount of developer interest across the United States. Yes, it's dominated in California and the West and Texas, but certainly out east, New York, Pennsylvania, and somewhat in the Midwest as well, we see a whole lot of developer interest in storage as well. Now, I wanted to take a few moments to dig into what we're seeing in terms of proposed hybrid projects in the queues. Like I said before, I think many of us are starting to consider hybrids kind of the power plant of the future in the United States. So just this chart on the left shows the total capacity in the queues for each of these different generation and storage types. But the darker bar, again, represents the portion of that total capacity that is in hybrid configuration. And it's just, again, remarkable, 42% of the solar capacity in the queues is in a hybrid configuration. And again, almost half of the storage in the queues is paired with some kind of generation. Now, just looking at the different types of hybrids that we see in these interconnection queues. That's shown here on the right. This is kind of could be a confusing figure, but each of these grid cells or each square kind of graphically represents about 1 gigawatt of capacity seeking interconnection. And what really stands out is this yellow type, which is solar plus storage, is by far the dominant configuration of all hybrids that we see in the queues. So yes, we have 12 gigawatts of wind plus storage. We have some wind plus solar, but really, we have 280 gigawatts of solar plus storage in the queues. And that, by the way, that 281 gigawatts actually represents only the solar capacity that is in these queues. So again, just remarkable interest in solar plus storage across the United States. Now we looked at the hybrid capacity that we see in the queues across various regions, and that's shown here. Again, I'm not going to spend a whole lot of time going through each of these figures, but what's, again, I think most remarkable here is that in California ISO, 95% of the solar capacity that is seeking to connect to the grid is paired with batteries. So really, if anyone who's building solar in California is doing so with battery storage or some kind of storage combined with that project or co-located with that project. Similarly, the West region is very, very high penetration of hybrids among their solar capacity in the queues. Okay, so now I just wanted to spend a few minutes. I think what I've shared so far is sort of maybe the good news and the exciting news from what we see in the queues, but there's sort of another side to that coin, and that relates to the completion rates of projects in the queues, and also the duration or the amount of time it takes for projects to complete the interconnection process. And these are all of great concern, I think, to a lot of clean energy and storage developers. So first of all, what we tried to do is analyze what percentage of projects that enter the queues actually reach commercial operations. So as I said earlier, a lot of projects coming into the queues are actually withdrawn. And what we found historically is that actually about 72% of projects that have entered the queues have actually withdrawn. And only about 23% of those projects that first requested or first entered the queue from 2000 to 2016 have actually been built. So we see pretty low completion rates over time. And there's some concern or some evidence that those completion rates might be declining in recent years. Now, those rates, again, vary, of course, by region. This is a lot of spaghetti noodles in different colors over here on the left, but you can definitely see, some regions have historically done better than others. And I'll show this on a map in just a moment. Similarly, we can see that different types of generation have higher completion rates than others. Unfortunately, I don't have this broken out for storage. We haven't done that analysis yet, but that's something we'll be doing in the future. But for example, wind historically has only had 20% completion rates for projects in the queues, and solar was even lower at just 16%. As promised, I did show these completion rates across all the different types of projects, so storage, wind, solar, gas, whatever, these kind of historical completion rates by region. And I think what's remarkable here is that there are only 2 of these kind of regional markets or ISOs, ERCOT in Texas and ISO New England up here in the Northeast, that have had historical completion rates above 30%. That's not a very high bar. And meanwhile, California ISO, New York ISO, and the non-ISO West have all had completion rates below 20% historically. So it's overall pretty low completion rates. And maybe that's due to a lot of speculative projects in the queues. Maybe that's due to very high interconnection costs or long wait times. So the duration or the amount of time it takes for projects to move through the interconnection queue, complete their interconnection studies, and actually, be approved for interconnection or have an interconnection agreement has become a real issue. And that's what I'll spend the next couple of slides discussing. So first, just to share a little bit about the duration from an initial interconnection request or when they entered the queue up until the point of a signed interconnection agreement. So this black line just shows the median amount of time that this takes in months. And you can see, you know, it popped up around 2012 or so, dropped around 2015, but has been increasing pretty steadily since 2015. And a typical project in 2021 took over 3 years to go from an interconnection request to an interconnection agreement. And that's not even, you know, reaching commercial operations. That's just that you have a contract to interconnect. Now, I just also wanted to show what happens after that interconnection agreement. Unfortunately, we don't have a whole lot of data. Here, we only had 3 ISOs, California, Texas, and New York. But you can see on average, it can take 2 years after signing an interconnection agreement to actually go on and reach commercial operations. And in California, recently, it's been taking much, much longer. A typical solar project in California built in the last couple of years might take 5 or 5.5 years to reach commercial operations, even after they have a signed interconnection agreement. So we have some real significant delays in this process that need to be addressed. Finally, just to show kind of the typical duration for the whole process, going all the way from your interconnection request up until the point where you reach commercial operations. And again, you can see just a pretty clear increase in that duration over time. If you were a developer that built a project between, say, 2000 and 2010, that whole process might have taken you about 2 years. And now, you know, for projects that were built in 2011 through 2021, the typical project could take 4 years to go through the same process. So we're seeing a pretty substantial increase in the amount of time this takes. So with all the backlogs and bottlenecks and problems that I've highlighted here, what's being done about it? There are a number of initiatives going on. I just want to highlight two or three key aspects that are going on at the federal level in the United States. Many of you are probably aware that the Federal Energy Regulatory Commission, or FERC, released a advanced notice of proposed rulemaking, or ANOPR, back last July, that was focused on transmission planning, cost allocation, and interconnection. That they followed that up this April with a notice of proposed rulemaking that takes that one step further. And that was designed to improve transmission planning and cost allocation, but did not directly address interconnection. So I think most people who study this space are expecting a standalone, another NOPR, or notice of proposed rulemaking, focused on interconnection soon. And then the second thing I'll highlight is that the US Department of Energy also has a brand new initiative focused on interconnection for wind, solar, and storage. That was just launched. We just actually had our kickoff webinar with the Secretary of Energy earlier today. And it's designed to enable faster, simpler, and fairer interconnection of solar, wind, and storage. So just to highlight a couple conclusions, and then I think we have some time for Q&A. It's just an unbelievable amount of capacity in the queues seeking to connect to the grid in the United States, representing a real transformation in the way we generate power. And we have a really substantial amount of standalone and hybrid battery capacity or storage capacity in development. And also, as I mentioned, you know, hybrids really comprise a very large portion of new projects being proposed and seeking interconnection. A lot more to say here, but to keep it brief, I'll just kind of leave one take-home point, which is that the capacity that we see in the interconnection queues, you know, it's over 93% clean electricity. That's already enough for the United States to reach an 80% clean electricity share by 2030, if that capacity were to be built. But of course, we know that not all of it will be built. Historically, less than a quarter of the proposed capacity actually has reached commercial operations. So a lot of work to do, but perhaps there's some promise in the queues. So glad to take some questions now. I think at least one has come into the chat or the Q&A, yeah. So we could start there.
Thank you, Joseph, for your presentation. Very interesting. I'll be actually interested to see if other technologies, like renewable or otherwise, have different completion rates. You know, I think that'd be very interesting, but that's probably, you know, something for another another session. But someone asks, so Kyle Buchanan asks, why do you think lithium-ion batteries occupy the majority of energy storage queued for interconnection agreements despite the high costs? There are more cost-effective utility-scale energy storage methods currently. So what are your thoughts on this? Why do you think lithium-ion makes up the lion's share of this queued capacity?
Yeah, actually, maybe I misspoke there, and I should be clear that, you know, unfortunately, in the interconnection queue data, they typically don't provide detailed information on what kind of battery chemistry, or even in some cases, what type of storage is being proposed. So, you know, I think in many cases we just have to infer that. Now we do, if it's, for example, pump storage hydro, you know, that's clearly indicated. We usually know if it's battery versus other types of storage, but we don't always know, again, the battery chemistry. So
yeah, you don't know what kind of battery, you just know it's a battery, and that's it. And another question, so Martin Hersfeld asks, does this data include behind the meter behind solar paired with storage?
That's an excellent question, Martin. And yeah, I apologize for not clarifying that earlier. It does not. So yeah, I mean, that's even, you know, more good news that, you know, that this really what we've captured in these data and analyzed here is just projects that are connecting to the transmission system. So it's not distributed energy resources, not behind the meter. So, but that means there's even more that we're not capturing here. So yeah, I think that's an exciting space too. But really, yeah, in terms of the 427 gigawatts of storage that we tabulated here, that's just you know, front of meter transmission scale resources.
Brilliant. And then Gordon Bayer asks, how can we access the new DOE I2X?
Yeah, thanks for that question. So I2X, that's the Interconnection Innovation Exchange. That's our new program. They have a website. If you search, you know, Google or your preferred search engine for DOE Interconnection Innovation Exchange, you'll find it. And I'd also be happy to follow up with the you know, question asker. If you want to shoot me an email, my email is shown on the screen here. Can send you those links directly. But yeah, would love to have you know, more partners on that project. It is really a stakeholder engagement, and it's a partnership program. So DOE is seeking, you know, to partner with developers and practitioners and, you know, regulators and utilities and ISOs, so to really solve these bottlenecks and issues.
Brilliant. Right, so a question by Christine Lan. What are some of the issues delaying CAISO projects going from GIA to COD aside from supply chain issues?
Yeah, that's a really great question. Now, that's something we would like to unpack, and I think it requires kind of a new analysis, a new study to really understand. But we hope to do that. I think in the future, we have plans to do something like a developer survey to understand, you know, what are the causes of these delays. But some things we suspect, in particular, maybe in California, California has really stringent environmental requirements. So maybe getting through kind of the local permitting for environmental and kind of local approvals could take a long time potentially. There's also procurement factors, or you know, securing the offtake agreement. So it could be that some of these projects submit into the interconnection queue and work all the way through before they actually have an offtake agreement, or, you know, a buyer for the power or for the project. So that could be a potential issue too, where, you know, you have projects getting an interconnection agreement but not actually having an offtake agreement, and that could take some years afterwards as well.
Okay, brilliant. And Lynn Polis Laurent asks, do you include in your study the interconnection queues of non-ISO entities?
Great question. Yep. And again, I apologize. You know, I skipped over our kind of data and methods slide, and for the sake of time to get to the good stuff. But that is something I should have mentioned. We collected data for all 7 ISOs, but also for 35 non-ISO utilities that, yeah, are part of WEC. So kind of that west region that I showed was made up of a bunch of different utilities that are part of WEC. So yes, the short answer is yes. We estimate that our data collection effort here probably covers about 85% of the United States electric load. It may be a little bit more than that, but yeah, so we're not capturing 100% of the interconnection queues in the US, just a lot of the smaller utilities that are not part of ISOs. It's kind of just a lot of effort to gather all these data, but the short answer is we think we gathered a whole lot and a representative sample of it. Yeah.
And then we'll answer a last question, and then we'll start wrapping up. So Laurent Namies Leonard asks, CAISO seems to have several deliverability constraints all over the system that will require several years to resolve. How will it be able to integrate such large amounts of storage given these constraints?
Well, yeah, I think that's another great question. And I don't think I know the answer to that directly. I guess I would just pose a couple of things. Now, one is at the same time that California has all these projects proposed, for new generation and new storage to come online, it also has projects that are potentially retiring, and whether those are fossil projects or potentially the Diablo Canyon nuclear plant, and that might open up new space on transmission lines in CAISO and enable a lot of opportunities for new renewable generation and storage to come online. I also would just say I think some ISOs are being a little bit more creative in utilizing and siting storage proactively and creatively to reduce the need for transmission expansion to some degree and reduce congestion on transmission lines. So perhaps the CAISO can do that as well. But yeah, I can't say that I have the expertise to know exactly how they plan to do that.
Joseph, thank you very much for your input today. I think we will, time has come for us to bring this workshop to a close. But yeah, it's been a great presentation. So to everybody who is in the audience, you will get an email with the slides, and there you could get Joseph's contact details. You can write to him and ask him any questions that you might have on this study. I might actually send you a few questions myself, Joseph, because I think you really showed. I really liked the presentation. You really showed a lot of the trends that we're seeing in the US right now. So I think there is a lot there that could be unpacked. And yeah, well, Joseph, I don't know if you'd like to say a couple of words before we go to the audience.
Yeah, well, thanks again for having me. I guess just kind of my takeaway from the analysis we've done here, I'll say one more remark is just that it's so exciting to see this energy transition happening in front of our eyes, but I think we really need to reform the way that we develop and expand our transmission system in the United States and the way that interconnection occurs if we are to realize kind of the potential that we see in the queues. So it's going to take some more work to resolve these issues, but there's definitely a lot of great potential.
Thank you very much, Joseph, and thank you to everybody in the audience who've been with us today. I hope to see you again here at the webinars and the workshops that we do. They're all free to attend, so and you'll learn a lot. So there is no reason not to. All right. So